I think we may be live. We may be live. Hello, everyone. Joining us again here for our day 2 of our free Easter revision course. We are going to do the second half of Core Pure. Who have we got in the chat? Everyone is back from yesterday. We're trickling in on this fine. What day is it? Monday? Yeah. Wednesday. It is Wednesday, 10 o'clock. What else would you want to be doing, eh? Do we still have Guy in the chat? Is he lurking? That is, we've got the main man himself who will be taking us through FM1 on Friday in the chat somewhere, possibly, maybe. Je ne sais pas. CubeCore Shruti, hello. Golsey, we are doing further decision. Well, we're doing D1, right? So there's the D1 ERC stream is on Sunday, but that is part of the full ERC paid package. So I'll be putting up links for that if you are interested, but that will be on Sunday with the mighty Guy Does Maths. So there we go. Bonjour, Historien 15, bonjour. Who else is in there? Alice is back. Hello, Alice. Meme, oui. Did I see... Who else is around this morning? Who's been hanging out with Charlie there? Who's got his offer from Warwick to study maths, which is amazing. I think I applied to Warwick, actually, back in the day. Cordelia, hello, of the concept. The mighty M's of EMS is, of course, with us. Am I Australian? No, how am I Australian? No. I like to think I do. What? No. I am British. Forgotten my options? No. So hang on. Okay, let's see if we can do this. I applied to Oxford, Bath, Bristol, Warwick, Sussex. I think it was. I basically went down the top, however many, and then at the top of the leaderboard for maths at the time. CubeCore, who decided to make the banner at the bottom scroll when the whole text play can fit in there in one go? Me, because it's funny and I like it. And it makes me feel professional. The link to the masterclass. So I will pop it up now as people trickle in. But if you want to go check out how the masterclass works, you can sign up with this link here. That will allow you to sign up to basically the last month and a bit of our main course, where we'll be going through exam prep, basically, essentially, is how that works for us. All right, so that's, if you want to scan that in, I'll go through pricing and the structure a little bit more later today at the end. But there we go. So here we go. The link for that if you are at all interested. So who have we got? Just trying to catch up. I can't read and talk at the same time, apparently. Michael, what, you woke up at 5 and haven't had breakfast? That's absolutely mental. That's mental. Although I have been known to wake up at 5, but that's just the body. Again, we got a little bit of sunshine on the green screen behind us, but that's because it's a beautiful day and there's only so much I can lock myself in a room. So, yes, absolutely. Nick buffering. You just got that on standby now, CubeCore, do you? Just got the Nick buffering emoji ready to go. It's fair enough. It is fair enough. So remember, if you've got some other friends in your class that aren't on here, you can ping them the link, because I have made this a public stream this time, nice and early. So just ping them the link so they can hop on and just have me on in the back. Soothing voice that you can just crack on with household chores as well as it's going on. Ems, 20 minutes ago out of bed. That is mental. Rylas, the previous streams. So for that, if you sign up to the full Easter revision course, you get all of the module lessons that are happening at for the rest of this week, but it also gives you access to the recordings of our previous streams. All right, so if you want to go back and rewatch yesterday's, if you want access to this one until your exams and beyond and into the summer, then you will need to sign up for the full course that I will put a link up for again later. Right, I think we have lots to catch up on today. If you scroll up in the chat, I did, in fact, put in the order of topics for today. I gave a quick breakdown earlier on in the chat, but we are going to get going. We are going to start by finishing off the differential equation stuff. Then we're going to do some coupled differential equations. We're going to go into some calculus with inverse trig and hyperbolics, and then some volumes of revolution. And that should get us to, hopefully, our first break of the day. Where can you access the mock papers? So, if you follow the little link in the description that will take you to the MyEdSpace platform where you can sign up for free. That will get you onto our platform for these free sessions, and the exam paper will be there ready to be downloaded. If you want the full work solutions and the solution paper for that, that's where, again, that is part of our full ERC package. This is just our little free section today. So yes, we are M's. So all of that, without further ado, I will leave the banner for a little bit until it gets in the way of my working, and let's go on. So we finished off with SHM yesterday. We're going to talk a little bit about damped oscillations, but really, by and large, this isn't desperately interesting because all it is, it's more like, it's just more second order differential equations, right? So if this is the motion of a particle, basically you can think of it that as these bits here are generating the simple harmonic motion, and then this part here is our damping term. All right. Now you can have a look at how this works, all right, comparing k to omega squared. But basically, because this gives us, right, lambda squared plus 4 lambda plus 8 equals 0 when we do our little term, our auxiliary equation, basically the k and the omega squared are going to tell us how many solutions we have, right? It will tell us how many solutions we have. Oh, first news of the day. So in our case here, right, so let's just have a look at our determinant. B squared minus 4 times 1 times 8, that is 16 minus 32, that is negative 16. Okay, so this tells me that we are going to get light damping, but what does that actually mean? This is lambda plus 2 squared plus 4 equals 0. So lambda is negative 2 plus or minus 2i. So my solution then is going to be x is equal to e to the minus 2t times a cos 2t plus b sine 2t. So what this actually means is that this e to the minus 2t, this e to the minus 2t is basically what it's going to do is it's the most common form of damping. You've got this e to the minus 2t curve, and I haven't really looked at the original this yet, but the e to the minus 2t is shrinking down the amplitude of our oscillations, basically. It mucks up a little bit with the periodicity, but not by a lot. And you can see a lot of this, right? So basically what we're saying here, right? Because if you have a look, the determinant here is k squared minus 4 omega squared, right? So if it's positive, right, that is light damping, right? So basically here, this is k squared minus 4 omega squared. Oh, here you go, heavy damping, right? Right, so that's heavy damping, and you end up with just exponentials. If it's equal to 0, you get something else. If it's less than, it's light damping. The main thing that you need to know are these terms. So yes, you do need to know what's in the box. I'm not going to show you all 3 different types. You can always look that up in a textbook. All right, what it actually looks like in terms of pictures, it's very easy for you to find. The main thing for me in terms of your exam revision is knowing these different terms. Okay? Oh, okay. There's a lot to do today, but let's finish this question. So this is an example of, is this heavily critical or lightly damped? If you have a look at what we've got going on here, which one is it? So is this light? It's light damping, right? So you've still got your oscillations, basically. You've still got your oscillations. So let's put this up here. You've still got your oscillations, but it is going down to 0. So this is vaguely what light looks like. This is light damping. Let's have a look. What would happen if you got heavy damping? Well, if you get heavy damping, right? If you get heavy damping, k squared is greater than 4 omega squared. All right, so k squared is greater than 4 omega squared. What you end up with is you will end up with essentially x is a e to the lambda 1t plus b e to the lambda 2t. But if this is set up, because this is positive, essentially because of how this is built, they should both be negative-ish. All right, or at least the bigger one will be negative if it's come from simple harmonic motion. Okay, so heavy damping, basically you just go like that. That is heavy damping. Yeah, Liam, that's what I'm explaining right now. So that is correct, right? So heavy damping is when your determinant is positive. That's what I've written here. So you end up with two different roots. And essentially, if it is proper damping, it's set up from a physical situation from SHM. They should really both decay. So you get this exponential going like that. And if it's critical damping, you have a repeated root, right? That is the determinant of 0. You get that repeated root. So you get x is a plus bt e to the lambda t. And again, normally the lambda is negative-ish, something like that. Okay? So it's gonna look something like this as well. All right, it's gonna look, because it might go up a bit. So early on this wins, and then it goes down. So you end up with something possibly looking up, right? Goes up and then like that. Again, it will depend very much on the case by case situation, but roughly that's what it means. But you do need to know these terms. Is it heavy? Is it critical? Is it light? And it's all about what type of solution you end up getting to our second order. Is it oscillations with decay? Is it, right? And then normal SHM just doesn't have that term there. Then the repeated root, you get that exponential decaying off that linear one, okay? Essentially, Pikachu, yes, if the auxiliary equation has two roots, it's heavy, one root is critical, and no roots is light. Very much that. What the picture looks like should look something like this if it is physically realistic, okay? Now, find the value of x when t is pi over 2. The particle starts at rest at the point where x is 2. I mean, we could figure this one out. X dot is minus 2 e to the minus 2t a cos 2t plus b sine 2t plus e to the minus 2t minus 2a sine 2t plus 2b cos 2t. So starts when x is 2. So 0, 0, that's a. And then if we look, and it's starting at rest, so x dot, let's look at equation 1, equation 2, equation 1, equation 2. What happens there? That's minus 2a, and then over here, plus 2b. So I think I get b is negative 2. Yeah, discriminants. Yep, sorry, I was looking at, what do you call it? Matrices just before this. Determinant, discriminant, the determinant, we'll call it that. Oh, let's remove the banner. Yes, sorry, I think it's been up long enough. Well, let's get rid of that. All right, so unless I have missed a trick because I'm trying to go relatively fast through this, don't ever try and speedrun your papers, boys and girls. There is a video up on this one, actually, if you want to see 2 attempts at me speedrunning a paper. It's actually quite fun. It's not in maths anymore, Nick. Yes, it is. Maths is in... How did you differentiate so fast? I do this a lot. I do this a lot. And it's just a product rule. Okay, find the value of... So we should get x is then e... Well, actually, it's 2e to the minus 2t times cos 2t. Neil has done it in so many ways. Yeah, but not for further maths. Neil doesn't do further maths. So when t is pi over 2, is b not 2? A is b. Yes, it is. Sorry. It is. Thank you. When t is pi over 2, then x is 2e to the minus pi. Whatever that is 2e to the minus p. Unless I differentiated this poorly, I think this is okay. X is 2, that's a 1, that's a 0, that's a 1. X dot is 0, that's a minus 2, that's an a, so minus 2a. That's a 1, that's a 0, that's a 2b, so plus 2b. So a is equal to b, so b is 2. I think that works. Is today going to be AS further maths? I won't fib. I don't. Again, I haven't really split it into AS and A2, and off the top of my head, I don't really have the breakdown for AS. So core pure 1 is AS, isn't it? What are we doing today? So volumes of revolution is for AS. What else have we not done? Vectors is today, that's AS. Linear transformation and matrices is AS. So there is a bunch of stuff today for AS. There we go. So we can get forced as well. Nick, isn't x equals minus 2e to the minus n? Well, we need all the cos and sine as well, right? Why would it be minus 2? It's just 2. What? So, goat. So, forced, you could have something on this side, but at this point, we are really starting to split hairs. If you have another function on the right-hand side, it becomes forced. But I'm not going to spend time on it because basically, at this point, right, it's barely simple harmonic motion. It's just mechanics. At that point, you've got forced motion, you've got damping, you've got a term on the right-hand side. It comes down to solve the differential equation. It's nothing special. You just go back to what we did yesterday and solve the differential equation. Okay, so Ems, if you haven't heard of it, it's probably because your teacher does it the same way, like thinks of it the same way as I do, which is it's not really a thing. It's just solve the differential equation. That's all it is. All right. So let's crack on. Couple differential equations, super easy. Differentiate one, plug into the second one. Right? It's super simple. Right, pick one, boys and girls. Are we going to differentiate 1 or 2? As Richard says, right? Just be aware that it's a thing, but otherwise you just solve it. Which one are we going to differentiate? Number 1 or number 2? I really don't care. We're going to differentiate number 1? Okay. So we are going to differentiate equation number 1. d2x dt squared is... There is also some really cool stuff you can do with matrices and eigenvalues, eigenvectors to solve this. But that is for a different... Not this course. Right. Now the thing is, we want to get rid of that one. How am I going to get rid of that one? Number 2. So we are going to plug in number 2. d2x dt squared is minus 5 dx dt plus 4 times minus 9x plus 7y plus 3e to the minus 2t. And it can be quite helpful to tidy this up already. So minus 5 dx dt, that doesn't change for me. Dx, what kind of silly sausage let me in? I didn't forget the last term. I'm just making sure you're paying attention. Minus 36x. Then there's a minus 2 plus 12. That's a plus 10 e to the minus 2t. And what I'm actually going to do is I'm going to rearrange that 7 times 4y. So hopefully that's all of those terms. 12 minus 2, we should be okay. Now, the reason I do that is because to rearrange for 4y, I can use equation 1. Nice and easy. So I don't actually make y the subject in number 1. I'm going to make 4y the subject, which is kind of cool. So this is just basically tedious. I would sum these questions up as tedious. Right, 4y. So 4y is dx dt plus 5x minus e to the minus 2t. So that should be correct. Dx dt plus 5x minus, right? And then we just need to tidy that up. So we end up with, I'm going to switch to dots, boys and girls. I'm going to switch to the dot notation. Plus 35. Can I get a quick check? So this is onto today's workbook, boys and girls. Can I get a quick check that this is the second order differential equation that we should be getting? I have limited space, so I am trying to do some working in my head, but that might create a few whoopsies. Yep, got that. Lovely. So now we just solve it. Right. So x is a plus bt e to the t. Yeah, absolutely. You can use whichever notation you want. Like the dot notation is much more of a mechanics thing, but it is so much lighter, and it is only for d by dt by bt dubs. Slurp. Right, now we need the so complementary solution, particular integral. These are so x is a e to the minus 2t, x dot is minus 2a e to the minus 2t, x double dot is 4a e to the minus 2t, just looking at what we've got on the right hand side. So we get 4a plus 4a plus a is equal to 3 if we plug that in. So I'm going to say a is 1/3. So basically from here on out, it's just a case of solving. All right, it's just a case of solving your differential equation. That's all it is. It's just a case of taking everything that we did yesterday and solving that second order one. So this double substitution, right? This is the interesting bit. If you're going to differentiate the first one, you'll end up with a dy dt. You use the other one to get rid of that. There's a y left. You use the original equation to get rid of that. It will always be that way. So, and if you've differentiated the second one, it will be flipped. You will differentiate number 2, use number 1 to get rid of a dx by dt, and then use number 2 to get rid of the x term. You can try it out. It will work absolutely fine. But it's always the same way. I tidied it. I just tidied it up. From there to there, I tidied it up. I'm also using the notation that dx by dt is x dot, if you haven't seen that one before. It is pretty long. It is what it is, right? Hopefully you also get that a is 1/3 whilst I clear a few things up. Those of you that are doing it along with me are catching up. How did I tidy it? Well, look at the dx dt's. Minus 5 dx dt, 7 dx dt. So that is 2 dx dt's, and I moved it over to the left-hand side. Negative 36x plus 35x is negative x. Move it to the left-hand side. I expanded, collected, and tidied. That's all it is. Okay. So what we've got here is x is a plus bt e to the t plus 1/3 e to the minus 2t. And really, what you should not do here is then go and try and do all this again for y, because these are coupled. They are linked. So we're going to share the A's and the B's. I have two equations, 2 bits of information. I have 2 unknowns. We are good. We cannot generate any more unknowns. So how am I going to find y? Ems, I will check that. Okay, let me make a note. More space in workbook. I'll pass that on to my person that edits these into the workbook. So we don't sub it into number 2. Number 2 basically gets used here. And then after this, you can trash number 2. After this point, you can trash number 2 because we're going to use number 1 again. And specifically, we're going to use this format. Remember, for y is dx by dt plus 5x minus e to the minus 2t. So that's what we're going to do. We are going to use number 1. So basically, if you are differentiating the first equation, the other one gets used at this point, and that's it. Okay, that is it. So we are going to have to fiddle around with this. 4y is dx dt, which I don't really want to differentiate dx dt, but I'm going to have to. So differentiate the first one, keep the second, plus a plus bt e to the t, plus 5x plus 5 times a plus bt. No. There we go. Plus 5x minus e to the minus 2t. Now then, we do want to simplify this a bit. Okay, we do want to simplify this a bit. Do tell me if you think I have missed something. I think we're okay. I'm going to put a little box around this because it's getting lost in my working. Don't be afraid when you're working to box things, highlight things, right? You can take colors with you just for your working. Just make sure your solution itself is in nice black pen, all right? But you do want to be able to draw your own attention to your own working because otherwise it can get a little bit funky. Yeah, Tonino, it is, right? We take this, right? Once we've got our expression for x, we are plugging it back into our rearranged version of the original equation. So that does involve differentiating and plugging it back into here. Now we can... Yeah, Dylan, right. Remember our original equation that we differentiated here, number 1. Remember down here, we rearranged it for y. So I will do that more explicitly here. You can rearrange that for 4y is dx by dt plus 5x minus e to the minus 2t, if you rearrange the original equation, right? That is what we are then going to use. That is what we are then going to use to find y. So we got our general solution. We've got our general solution for x. We then plug it back into that rearranged version of the original equation. Now, in there is a dx dt, so I differentiated it, right? That there is my dx dt. 5x, unless I'm very much mistaken, should be there. And then minus e to the minus 2t is here. And then it's a case of tidying it up. It's not particularly pleasant, but maybe we try and find a and b first. So when t is 0, x is 0, y is 0. So x equals 0. So let's put t as 0 into here. So that disappears, a plus a third. So I get a is negative a third. And then we are told that y is 0. Now y is 0, so that's a b. This term here, when we plug in 0, will give me a. Minus 2/3 from this term. I pick up another 5a from here. Another 5/3 and a minus 1. Oh, that's quite nice, because unless maths has changed massively in the last few years, these terms cancel out. Ooh, do these terms all cancel out? That's pretty cheap. That's pretty cool. I like that. So we get b is minus 6a. So I get b is 2. I get b is 2. And now it's a tidying up game. So x is minus a third plus 2t e to the t plus 1/3 e to the minus t minus 2t. Yes. And then y, right, let's tidy this up. Okay, so a is minus a third. So what do we get for constants? I get 6a, which is minus 2, plus b. Oh, does that disappear? I think it does. And then 6b. Not now, Nightbot. I think that these are my answers. I think. Oh, no, because that's divided by 4. In the interest of time and you not sat here watching me try and do lots of algebra, um, I suggest you just double check this and take your time going through it. That y looks suspiciously easy. I get b is 2, Charlie, because we got a is negative a third, as far as I can tell. I get a is negative a third, and then the y one, I probably should have tidied it first, but I get the y one telling me that b is negative 6a. Dylan, I just plugged in my a and b into my y equation here, and I tidied it up. But again, I'm trying to do it mentally, which is possibly a terrible, shocking, bad idea right now. You guys get b as negative 2. Ah. So to get a, I just put in my initial conditions, boys and girls. Right? That's how I got a, KP. Right? I just put in my initial conditions, the ones that I was given here, into my expression for x and my expression for y. These questions look short, right? 3 lines, bosh. But they take quite a bit of working. Can you get the mathematical modeling ones? Yes, yes, you can. It's the same question, just with a bit of decoration. That's all it is. Same question, bit of decoration. That's all. Okay? Right, we have a lot to cover today. So please finish this up in the same time. If you did get a different one, let me know. But I'm going to crack on. Right, inverse trig functions. Let's talk about them. Basically, you need to know how to differentiate them. I'm not going to derive them. Again, that's not the point of today, but these are the ideas that you need, and you do get given them, right? You do get given them. Bum. I have this up today so you can see, right? Formula sheet, you do get given all of these. So you need to be able to differentiate and integrate. And quite frankly, I won't lie to you. Do I remember which one is arc sine, which one's arc cos with a plus or a minus? No, I do not. I do not at all. Do I remember which way round it is for arc sine, arc cos, and arc tang? Nope, I do not. If I don't have access to a formula sheet, I derive them every time. So the outline for deriving them is just... I will show you the setup and then you can figure it out on the fly. Of course, all we do is implicit differentiation. So we take sines of both sides. And then we are going to use that cos y is... Do you know what? After having said that I'm not going to derive it, there we go. This is our derivation for arc sine. And there we go. This is also how you differentiate ln. It's how you differentiate basically any inverse function. It's how you can prove that the rules for differentiating polynomials works for fractional indices, for example. It's all the same. So it is fairly quick, right? And it's the sort of thing you will derive in normal maths with implicit, but we need to be able to integrate with it quite comfortably as well. That's all it is. So find the tangent to y equals arcsine 2x when x is equal to a quarter. Well, when x is equal to a quarter, y is arcsine of a half, which is pi over 6. dy dx is 2 over square root 1 minus 4x squared. All right, just using your chain rule. We're not going to spend a lot of time talking about chain rules or anything like that. Okay, because we are further mathematicians. We have other things in our lives. Kim Patel, what's 2x? Oh, yeah. Well, this was the derivation for arcsine x in general. Then you can start doing your chain rules, right? I wasn't doing it for arcsine 2x, right? The main thing is how to get these ones if you've forgotten them or you don't have a formula sheet. That's all. 4x squared, that's going to be a quarter. So we get 2 over root 3 over 2. Because that's square root of 3/4. That's 4 over root 3, so that's 4 root 3 over 3. So y minus pi over 6 is 4 root 3 over 3x minus a quarter. Core skills, the only thing that gets added is this. All right? That's it. Right? Core basic skills. Now for integration, again, if we bring up what you get given in the formula sheet, personally, where is it? Personally, right? Again, I say I don't remember them. I don't. Half the time I have to look them up, or I just rederive them if I'm in a situation where that happens. The reality is, of course, that I'm not a student studying maths. When I'm doing this for myself, when I'm doing a question for TikTok, for YouTube, whatever it is, if I need to remember these, I will look them up. You are able to. That is the reality of the age we are in. If you aren't able to do that, derive them, right? Like memorizing these is a sucker's bet. So you do have all of these in here, but I am going to do this one from scratch, right? But you do have them where they're giving it to you in terms of a squareds and x squareds. Now, there's a couple of ways we can do this. I'm going to do it in two different ways for number b. I'm going to do it for two ways in number b. So first of all, I'm just going to do number b myself, right? Now, what I want is I want a 1 here. You'll notice the key thing for all of these is the 1. So what we're going to do is I'm going to take a 9 out. Because that is 9 times the integral of 2 over 1 plus. And I'm going to write this as 2/3 x all squared. All right, so you factorize out the 9 because the key thing we are looking for here is that. All right, that is the key thing we are looking for here. So what I'm left with is 9 times 2, these two. And if I look here, this is an arctan. It is arctan of 2/3 of x, but because of that 2 over 3, I need to multiply it by 3 over 2. Shouldn't it be 1/9 out? What you on about? Oh, sorry. Yeah. Good call. Good call. That was looking real wonky for me there for a second. Thank you. Right. And what's interesting here is that the 2's cancel out. The 9, I knew that was wrong. There we go. Much better. So we end up with, oh, purple. All right, we're going to stick with the purple. Arctan 2/3 x, putting in our plus c. Now the other option is, let's freeze the screen so I can do this. Hope it doesn't muck up completely. It doesn't. Very good. So if we take the option from the formula booklet, it's actually quite different. They want the 1x squared. So instead, we're going to take the 4 out. We're going to take the 4 out of the denominators. Let's just make sure. Let's just make sure this comes out, right? Let's just make sure this comes out. I'll double check, see if it's gone a little bit wonky in a second, right? So if we have a look at this, I've got the 1/4, I've got the 2, and now I've got a squared and an x squared. So I do, a is of course 3/2, so that is going to be 2/3, 1 over a, arctan of, again, a is 3/2, 2/3 of x plus c. And if you have a quick look at all the cancellations, bosh, bosh, bosh. So a is 3/2, absolutely a is 3/2. But notice the formula is divided by a. So it's divided by a. Okay? So it's an interesting little juxtaposition, right? So how do I know I can't have a coefficient for x squared? So it really does depend, right? If you are just going to do the sub for yourself using what you know about differentiation, the key thing for the derivatives is that 1. So what I do is basically I make the 1 happen by correctly eventually factorizing out the 9. And then it's a quick u substitution. All right, but that's one that we really should be doing ourselves real quick here. We're going to use u equals 2/3 of x. Oh, that's in the wrong place, actually. All right, that's what we're doing here. Essentially, we're making a very quick linear u substitution. Okay, that's all that is. And if you're going to use what they give you for the integration here, they've basically done all of that for you and given you this result. It's not my favorite, but I suppose there is still, all right, so we're going to create a singular x squared because they want the a squared there, which is what we do by factorizing out the 4. And then we can crack on. You can see that a is 3/2. Yep, if you are happy using this, you can do. But again, I want to make sure that you are prepped for situations where you don't have it. Again, guerrilla maths, I suppose. But yeah, that's the idea. What does the end? So that was a 4. That was a 9. So if you have a look here, that was a 1/9. Let's make it a little bit clearer. All right. And then it was the 2 and the 2 cancel out, the 3 and the 9 cancel out, and it gives us 1/3 arctan 2/3. But how do we know it's singular x squared? Well, look at the form they've given you, right? This is what they've given you, right? This is the one. This is the integral you get given in the formula booklet, if we refer to it. I know that Great Neil doesn't love the formula booklet, but sometimes it's needed. We need to know a lot. Right? This is legit what they give you. So it's a squared, something squared plus 1x squared. So if you're going to use this result, you need that 1x squared. You do. You do, you do. And you could fudge it by making an u substitution if you didn't, right? We could also have done, if you really wanted to, instead of factorizing out the 4, other option, or you could have made the substitution u equals 2x, and that would have given you a u squared. You could have done that. You could absolutely have done that. I mean, is this harder than A-level maths? Because all you're doing is you are taking results that you know how to differentiate or how to integrate, and you're adapting them with very quick u substitutions or just basically mini chain rules. That's all it is. Oh, Shruti, like, so for normal maths, I have loads of beef with the formula booklet. I do. But for further maths, by the time, and especially how easy it is to get the inverse hyperbolic trigs and the inverse hyperbolics mixed up, I think it is fine. I accept, like, it is so easy to get them mixed around. I accept the existence of the formula booklet. All right, but really, that's it. All right, just take your time, pick a method, either do inverse differentiation or use the formula booklet where it's done for you, but just make sure you have the correct coefficients. That's it. Okay? Right, hyperbolic functions. Now, we are going to do number A without referring to the formula booklet, because again, it does help you out a little bit, but if you don't have access to it, you can derive it. So we've got the hyperbolic sine and cos. We mentioned these yesterday, and they're basically the non-complex extensions of cos and sine. That's what we spoke about yesterday. You can see the absolute parallels between cos and sine that we were working with complex numbers. So there they are. We did, hey, what if we take all the i's out? And everyone went like, cool, man, let's take the i's out. And we just call them hyperbolic. Why are they called hyperbolic? Yada, yada, yada. They're parametrics for a hyperbolic. Join me for FP, for Further Pure 1, if you want to talk about that a little bit more. There is a very good reason they're called hyperbolic. But there we go. That's what they are. Yeah, Pikachu, like if the question isn't saying prove this result, you can use them. That's not a problem. Right, so shine x is 2. If we want to solve that, well, there's two ways. Either, well, we can set up our own little equation. And what we're going to do is we're going to create a quadratic because we as well cool. And we can create a quadratic because we are well cool, man. And there we go. Cheeky hidden quadratic. Now, as an absolute core model, why do I take the plus root 5 and not the minus root 5, cheeky cool kids? Oh, yes is way ahead of me. So what's yes saying? Yes 9516. Not any yes, but yes 9516. What you up to? It can't be 2 minus square root 5 because then you're taking natural log of a negative number. Absolutely. We are remembering here that e to the x has to be positive. So e to the x is 2 plus root 5. So x is ln of 2 plus root 5. I think this is something you need to be able to do, really. All right, you do need to be able to do it. But I will point out that they do give it to you. All right, you do have access to that. Okay, so if you want to take arc sine of something, it is ln, right? So we could have done that. It is ln of 2 plus square root of 2 squared plus 1, and you would get that same answer out. All right, you would absolutely get the same answer out. All right, now in the same way, solve. Now this one here, cos x plus 2 sine x, there is a way to do it. If we were doing this with normal trig functions, you would go and make the harmonic form. Go for like and we could do it, right? We could absolutely turn this into an r cos x plus alpha. Don't. That is insanity. Therein only madness lies. But we can do it. It would be possible, right? Possible, but a bad idea. All right, not unlike bungee jumping without attaching the elastic band to your legs. It's possible, but it's a terrible idea, and you'll probably only do it once. Yeah, there's no reason you can't reach it. right? There are compound angle formulas for cosh and sine, so there's no reason you can't do it. It's just not nice. Instead, what is much, much better is just writing them as exponentials, right? So I'm going to times everything here by 2e to the x. Don't judge me. So that will be 3e to the x all squared minus 2e to the x. That's minus a half. So I think that's what we end up with. The logic is the 2 is to get rid of the fraction. The 2 is to get rid of the fraction, and the e to the x is to get rid of the e to the minus x, and we end up with a hidden quadratic. That's the reasoning. So if you're trying to solve one of these, you want to get rid of the negative exponents, you're going to make a quadratic. Does anyone have any beef with this? I hope not. Because it comes out nicely. So we get e to the x is minus a third, which makes me very, very sad. So that's impossible. Or we get e to the x is 1, which is x is 0. That is our only solution. You've got no idea what's happening. These are just chilled little functions. Now I'm just going to turn my cat this thing off. My wife also hates how much I glug when I drink, so there we go. Right, and number C, find cosh 2x in terms of cosh x and sine x. Now, the other nice thing is, right, that you could derive this just using exponentials, right? It is absolutely possible. But who can tell me what the rule is for adapting? Who can tell me what the rule is for adapting the compound and double angled trig formulae into the hyperbolic version? What is Osborne's rule? Everyone has to have a name, right? I hate this. The Osborne's rule. I don't care who came up with it. It's ridiculous. When there's a sign, make it negative. Not quite, yes. Not quite. Yes, Rootchit. Product of two signs, change the sign. Do you know what? Let's see if we can get this. Where's my thing? Oh, that went away. I should have remembered to freeze it. There we go. Right, if there's a product of two signs, we change the sign. So cosh 2x will be cosh squared x. Now there's two signs being multiplied there, sine squared, so it becomes plus sine squared x. Okay? So, for example, I could have pinned it in the chat, but this is more permanent. So sine 2x is 2 sine x cos x. There is no product of two sines. You multiply a sine and a cos, but there are no two sines multiplied. So sine 2x is just 2 sine x cos x. And you can always check these. You can check them really easily just by using these. And it's super simple. All right? Super simple. This tells you, yeah. So it does. So they do have these in the formula booklet. This is not an exam question, right? This is me making sure that we're going to talk about all the things I want to talk about in hyperbolics. That's all, right? You might be asked to derive it. you might be asked to derive it. So if we wanted to derive it, again, we're gonna overrun today, by the way. I've made my peace with it. We're gonna overrun by a solid, possibly half an hour to an hour, right? Cosh 2x is e to the 2x plus e to the minus 2x over 2. Now, if you know what the answer is, that could be quite useful, all right? But I could go plus 2 minus 2, right? Plus 2 minus, do I need plus 2? No, I need plus 1 minus 1. So, because what I want is plus 2 in the fraction, which means I need a minus 1 out there. All right. And that becomes 2 cosh squared x minus 1. I'll let you figure out some completing the squares to prove that for me. All right. And then if you use this bad boy, if you use that bad boy, you will get the correct answer. Okay. Now, you do need to be able to differentiate and integrate using the inverse hyperbolics. But again, we're not going to spend tons of time on it because to help you out, you do get given them in the same way, right? You do get given them in the same way you derive them exactly the same as deriving the inverse trig functions. This is why it doesn't require a lot of time us talking about them, because it's the same idea with slightly different functions. Now, the key thing I want to draw your attention to is here. And again, if you differentiate, use the definitions in terms of ease, these are very easy to derive. But sine differentiates to cosh, cosh differentiates to sine, which is amazing compared to trigs, where you're like, hang on, I've integrated sine, so I pick up a minus, but if I differentiate sine, I don't pick up a minus. Hyperbolics, sine to cosh, cosh to sine, sine to cosh, cosh to sine, sine to cosh, cosh to sine, and everyone is happy. All right. But it does wreak havoc a little bit with the inverses in terms of how they are, like how similar they are, but you derive them in exactly the same way, and we're not going to derive them all. But you get given these results, you just need to be able to do them. So solve, but here we go. We do want these Lun versions, and this is very, very important. All right, this is important. So let's solve 3x's tanh of ln of root 2x minus 4x. Now there's a few things here. There's a few things here to unpick. There's two ways we can go about this. You could just use, if you wanted to, the definition for arctangent. So option one, we're going to do this in two different ways. Do this in two different ways. So we could say that arctangent of 3x is ln of square root 2 minus 4x. Now, why is that useful? Because if you use the definition of arctangent, that is 1/2 ln of 1 plus 3x over 1 minus 3x. If we multiply both sides by 2, but importantly for me, if I use the rules of lns correctly, it's almost as if they're important. I get rid of the square root. And from here on out, it is EZPZ. So what's that? 12x squared minus 4 minus 6 is minus 10x plus 2. There we go. So we should get x is 1/12 or x is 1. Do not fear. the main thing I will say is just be aware of which ones are in the formula book. All right, again, that formula there is straight out of the formula book. Okay. Now, mod x has to be less than 1. Mod x has to be less than 1 here. So the x is 1 looks like it might not work. All right, and there's actually a little bit more than that. Can you tell me why x is 1 is not valid? You can tell me why x is 1 is not valid. Good. So there's a couple of reasons, right? So number one, basically tangent is between 1 and -1. So looking at that, we need mod 3x has to be less than 1 because we take an arctangent of 3x. So that tells me that x has to be less than a third. So that's already a problem right there. Or when you plug x is 1 into there, square root of 2 minus 4 times 1, that is square root of -2, which makes me sad. Shut up, Nightbot. Okay, so that is our problem. All right, so it's that bit there that becomes an issue. Now, the other option, of course, is for you to remember that tangent u, I'm going to do it with u for now, is e to the u minus e to the minus u over e to the u plus e to the minus u. So, of course, maybe a less straightforward way is tangent of ln root 2 minus 4x. You could plug that in. That is e to the ln square root 2 minus 4x minus, and you could always write that as 1 over e to the ln square root 2 minus 4x. I'm not saying this is my favorite idea. Okay, I'm not saying this is my absolute favorite idea, but it's an idea. And then you could multiply the top and the bottom by that. So this should end up with 1 minus 4x over 3 minus 4x. All right, and it's basically because the e's and the ln's cancel out. And that itself needs to be equal to 3x. And I think we end up with the same equation. And you end up with the same equation. Don't know, just putting it out there that is a thing you can also do, because as soon as you've got sine or tangent or cosh of a ln, remember, as soon as you put it into the actual definition of sine and cosh and tangent, all the e's and the ln's cancel out. So that's kind of sweet as well. But again, we're not going to spend tons of time with it. We will be doing more and more exam questions throughout the exam masterclass as well, actual exam questions, to have a look and more practice on this. But we've got a lot to cover today. But having said that, we are going to look at this bad boy. This is from the formula sheet, so we got everything access to it. What do I do here? Because obviously this does not look at all like any of these. So what is the key that we need to look out for when we are doing integrals with quadratics? Yes, boys and girls. And yes, we are going to complete the square. This is absolutely right. It's in poor tent. So that is x minus 1 squared plus 9 dx. Few options for us, but again, we've got 1 lots of the x squared, which is very good for us, right? We've got this 1 lot of x squared. Now it's x minus 1. If you really want to, if you really don't want to deal with this, you make the substitution u equals x minus 1, right? If you really want to, you don't You don't have to. If you are feeling confident, you don't have to. All right, but you can do that. Now, it's square root of something squared plus something squared, which does look like this one. So that's what we're going to go for. Now, a is 3 because that's an a squared. So this is actually just arc sine of u over 3 plus c, which is arc sine of x minus 1 over 3 plus c. And that's it. All right, but complete the square. You may end up with a number in front of the squared thing. Do what we've done before. Get rid of it. Factorize it out or make it the substitution. But that's all we want. Don't forget the minus 1, Mohammed. Yeah, there you go. You caught it. All right. We are not able to spend tons of time today doing every single possible version of this. That is largely impossible. Sit down, do lots of practice. You need to. But it's all about recognizing that if you are doing anything, any integral, basically any integral with a square root of a quadratic in it, or a fraction of a quadratic or a power of a quadratic, I would always suggest completing the square. Super simple. That's where we're at. Am I teaching year 13 next year? We haven't quite decided yet. It is myself or Guy. So either I will be teaching the year 12 further maths next year, or and Guy will be doing year 13, or vice versa. Practice, 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 always. Practice is for everything. FM1, Core Pure, all of it. Just practice, practice, practice. Okay, so that is our very quick whistle stop tour of all the inverses, but basically anything to do with hyperbolics in Core Pure, with inverse functions, integration, differentiation, they give you everything you need in the formula sheet. I've tried to show you where it is, how to work with it. That is the best way for you to do it. Just sit down and plow through practice. Just through the textbook questions, all right? Like do the homeworks that I've set. If you're part of our main course, and I know only about 3% of you naughty students that are on the main course actually do your further maths homework, there is a whopping 10 exam questions worth of inverse hyperbolics waiting for you, sitting there waiting for you to do it with full exam solutions. Right. Volumes of revolution. Now, this is in the normal maths course, right? Nothing changes whether you want to integrate around the x-axis or if you want to integrate a revolution around the y-axis, it doesn't matter. Okay? Oh, I taught you in year 11, did I? Oh, what? Last, did I? When? How? Why? Which topic? Right. The region R is bounded by the x-axis, the curve y equals root sine x, and the line so. If you don't have a picture, let's do a quick picture. If you have a CG50, use a CG50. So sine is, it's going to look something like this, basically. It's going to look something like this. All right. Root sine actually doesn't exist beyond that. So we are going to rotate it about the x-axis. We're going to rotate it to create a rugby ball. Find the volume of the surface. So it is pi times the integral of y squared dx between 0 and pi. That is pi times the integral of sine x dx between 0 and pi. That is pi times, and making everyone very, very cross, I make that 2 pi. Yeah, that was so nice, right? But the real difficulty that comes in when you do this in further maths, in Core Pure, is that, of course, the different integrals that are up for grabs are nowhere near as nice for you. They are nowhere near. So let's have a look at this next question, which is possibly a little bit more interesting. The region S is bounded by the y-axis, the curve. And you know what? Let's do it. Let's plot this thing. Let's plot this bad boy, just so that we've got an idea of what it looks like. So we're going to bring up our CG50 or equivalent. Again, I don't want to be a massive shill for Casio, but I do really enjoy my CG50. 1 minus 4x squared. Oh, that's 1 plus, isn't it? Yep. Over x squared. Okay, thank you. Let's just go for our initial zoom and see if that helps at all. Okay, so we're going between okay, that's what it looks like, guys. Fine, whatever. We're going to rotate it. So let's do a quick sketch. Right, it looks something like this, apparently, this graph. I'm working on it, Liam. Oh my gosh. Oh my gosh. Right. Give me a sec. All right, so what we're doing now is we are rotating it around the y-axis. So we need, our volume is pi times the integral of x squared dy. So what I want is I want to sub in x, all right, much like I subbed in y. So I am going to have to make x the subject. So we'll start by squaring, and this is where it gets more complicated for us, right? X squared y squared plus 4x squared. But to be fair, making stuff the subject like this is something you were doing at GCSE. But do not kill yourself making x the subject. If you want to sub in x squared, make x squared the subject. Ooh! But here's the thing, though. Here's the thing. Again, not to be that guy, but see how it ties in with what we were just doing. We're going to be using this one. Nick was not buffering. Nick was making something happen. All right, straight from our formula booklet, we can use this. Now again, notice a singular x squared. We're working in y's. That doesn't bother us, but we can see that a is 2. Or you can sit down and make the substitution, factorize out the 4, whichever way works for you. But that is, oh, we're going from y is 0 to 2. So that is pi over 2 arctan of y over 2 between 0 and 2. All right, so that is pi over 2 arctan 1 minus arctan of 0. That's pi over 2 times pi over 4. So that should be pi squared over 8. Again, not to, I mean, they're free videos, so do check it out. If you want a little bit more in depth of what you can do with the CG50, there is a video on this channel about how to use it. But if you really wanted to, you could check your, oh. Now this is in terms of X. You need to obviously be able to jump around these a little bit. And yes, I'm very aware I haven't put the pi in there yet. And hopefully, and there you go. It doesn't give you exact answers, no, so you can't just use it. But when you've done a long question like this with lots of different moving bits, it's very nice to be able to check your answer, right? So ranks, yeah, I do rely on it. Like you can do it without it, right? But I won't fib to you. Sketching square root of 1 minus 4x squared over x squared by myself, it is not worth my time, especially in an exam. I know this is not available to everyone. I know it is not a possibility, but check out eBay, check second hand areas like this. There are various places that can source these tools for relatively cheap. Ask your school if you can get one through them for cheaper. But as if you are doing further maths and you are looking to do STEM later on at university, like a graphing calculator of some description is very, very useful. Guy is amazing. Guy is like a more grown up me. All right, but this is it. That's what we want to do for volumes of revolution. Now we can do it with parametric equations. I love doing parametrics. It's the Nick trick. So x is tan theta, y is sine 2 theta. Again, I don't really know what it looks like. I could spend time figuring it out. I could absolutely spend time figuring it out. But if I was an 18-year-old, 17-year-old, mucking about in an exam trying to figure this one out, oh, I mean, okay. Let's see if this works. I wouldn't want to be spending my time doing that. 2 tan t. All right, apparently that's what that looks like. Cool, apparently that's what that looks like. Awesome. Yeah, cube core. Like, so that's the thing. When I taught at Hills Road in Cambridge, that's what they did. They bulk bought CG50s and then they came in at like 70 quid a pop. So we are rotating around the x-axis. So I can draw the equivalent there, and we are doing this. We're going to take a break at past. So we're rotating around the axis. So we want pi integral of y squared dx in theory. But what's really cool, if you don't remember these, it's fine. How do I make it parametric? Now, in our case, it's thetas, d theta, d theta. Bosh, done. Missed it. All right, but that's the trick. All I'm doing is I'm timesing and dividing, multiplying and dividing by the d that I need. And that's it. That's it. It's a change of variable, y'all. That's all it is. So this becomes pi times sine squared 2 theta. I'm going to worry about just how awful this looks in a second. Now, dx d theta is sec squared theta d theta. Now, we do need our limits. Now, we're going from x is 0 to x is 1. I don't know, x is 1 there. So we do need to know the limits. Well, x is tan theta, right? So x is 0. That is tan theta is 0. That will give me theta is 0. X is 1. That is tan of theta. That tells me that theta is pi over 4. So we're going from theta is 0 to pi over 4. Now, yeah, let's write these in terms of sine and cos because this is scary. So that is 4 sine squared theta cos squared theta. Sec squared is 1 over cos squared theta. And what do you know? What do you know? They cancel out. And I'll remind you, of course, that cos 2 theta is 1 minus 2 sine squared theta. Like I say, being able to integrate cos squared and sine squared quickly is kind of a big deal. So that will be 2 minus 2 cos 2 theta. Brackets. Why do I want brackets? I don't need brackets. What brackets do you want me to have? Right, 4 sine squared, multiply it through by 2. Don't you go mucking with me. Pi over 2 minus 1. Oh, that's it. Sine of pi over 2 is 1, 0, yeah. Pi squared over 2 minus pi. And we're done. Simples. Integrand sign bottom to top. So long as it looks vaguely like an S. So you differentiate and integrate, Mohammed. Yeah, like literally it comes down to this. It's a change of variable is what it is, right? You are changing the variable from x to theta or x to t or whatever it is. But the way I like to think about it is just divide by d theta times by d theta. Bosh, we get the correct one, right? You'll notice if you cancel these out, you get the equations we had on the previous slide. I mean, that is quick and dirty, and pure mathematicians up and down the country are tearing their hairs out at the fact that I'm saying this. But you know what? It works. And if it's stupid and it works, it's not stupid. That is my family motto. The integrand is the symbol. Right. What have I got lined up? Let's quickly do mean value. That'll get us to 11:30, and then we'll take a 10-minute break. I need to power through a lot of stuff. Because what was my plan originally? Yeah, if we get through to the end of mean value, possibly improper integrals, that takes us to matrices. Let's go. The mean value is this. Essentially, it's a mean, right? Instead of adding up and dividing by the total, you are integrating and dividing by the length. That's all it is. What you are actually doing when you do a mean value, right? When you do a mean value, is say you've got your function here. What you're saying is, well, what if I had a box that had the same area? And that's the idea. You are saying, actually, right, what's the height of a box that will have the same area? And that's all you're doing. You're saying if I wanted just a constant function, a constant, that if I integrated that, I would get the same area. That's it. All right? That's all it is. That is the mean value. Why do you need this? Because it's in the exam. Because in the exam, myself personally, whether it's at uni, doing research afterwards, whatever it is, I've never had to use a mean value, but it is what it is. So if you want the mean value of this over 0 to 5, f bar will be 1 over 5 minus 0, the integral 0 to 5 of x square root of x plus 4. And that is it. Have you not? Am I booging? Is this mean value of a function? It's core pure 2. Chapter 3, 3.2. It's because it's not really a thing. You just need to know what it is. All right. And you just do it. You just do it. Oh, let's not sub it into a calculator. Let's make a very quick change of variable. U is equal to x plus 4. So this becomes 1 over 5, 4 to 9 of u minus 4 root u du. The reason I've put this in is also just to really highlight to you that one of the expectations of you as further mathematicians, hang on, is you are expected to be able to do these integrals quickly. Neil would hate the U sub. Well, what would Neil do? What would Neil do? All right. Neil can hate the U sub all he wants. This U sub is much nicer. So that is 2/5 times 3 to the 5 minus 8/3 times 3 cubed minus 2/5 times 2 to the 5 plus 8/3 times 2 cubed, whatever that comes out to be. Recognition. You do not recognize this. This is not a recognition. This is a standard way to get rid of the x plus 4 in the square root. None of that. None of that. Thank you very much. Recognition. Has Hokya been freed yet? No, Hokya never gets freed. All right, this plug into the calculator. Like, ain't no one got time for that right now. All right, I definitely do not have time for 3 to the 5. Lol. Ain't no one got time for that. But yeah, we go. You need to recognize this idea of a mean value. It's a basic one. What chapter is this? It is Core Pure 2. It is chapter 3, page 2, if you're using the Edexcel textbook, which is page 58. Again, there's no new maths in it, right? There's no new maths in it. So it's not a big thing to teach you. You just need to be aware of what it is. Right, improper integrals. We've got 4 or 5 minutes. We'll do at least one of these. We'll do at least one of these. Now, ain't gonna lie to you. I know when I do actual maths for myself, and no mathematician beyond doing it at A level does this in this proper way. No one does it, right? We vibe it a lot more. We treat infinity as a number and we're chill with it and it works. But you need to be able to do this properly. So an integral is improper if you've got infinity as a limit or it's undefined. So you've got an asymptote somewhere in it. So you need to be real careful. So number A, there is an infinite one. Otherwise, 1 over x squared has no problems. 1 over x squared looks like this. Don't know why this one doesn't get a nice one. That's 1 over x squared. We want to go from 1 to infinity. Bob, 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 bob. The main thing is the infinity. So what do? We're going to just go 1 to a. So how about we just integrate from 1 to a? 1 over x squared dx, which is of course minus 1 over x from 1 to a, which is 1 minus 1 over a. Okay? 1 over 1 minus a. What we do then is we take the limit as a goes to infinity of 1 minus 1 over a. And we see what happens to this as we let a go to infinity. So 1 minus 1 over a, well, that becomes 1 minus 0. So the integral is 1. Nice and easy. So if infinity is a problem, you just put in a or b or something else, right? Put in a placeholder for it and then let that placeholder get stupid big. All right, let that placeholder get stupid big. X over square root 9 minus x squared. I do believe there might be a little bit more trickery to this, but it should look something like this. Yep, looks pretty much like that. Why does one of your infinities look like a Q? Because it's an A. That was a really bad A. In your defense, that is a terrible A. So we'll have a look at that, the plus or the minus. We'll have a look at that in a bit. I think that's what we're going to do in C, possibly. But really, this would be, we are approaching. So actually, I'll show you that limit in a second. This is exactly what we're going to do here. So the idea here is that we want to integrate between 0 and 3, and I'm undefined at 3. My function is undefined at 3. So what am I going to do? Well, I'm going to integrate from 0 to a, x over square root 9 minus x squared. Now this one we are going to do by recognition. What I'm going to do is I'm going to multiply the top by -2 and divide by -2, because now that is the derivative of 9 minus x squared. Right. Buffering. Have I oversped here? Have I oversped? So we are integrating x over 9 minus x squared. So it's not arc sine, Kim, because you got that 2x on top. If you really want to make the substitution, I think something's gone wonky here. I need to check that. Sorry. There we go. Make the substitution u equals 9 minus x squared. These 2's cancel out. But this is going to give me 0, which I don't like. It's going to give me 0, which I don't like. Can someone spot the wonkiness for me? Where are you getting that 2 from? Because it's a square root, right? Differentiate this, you will see what you get. Differentiate this, you will see what you get. Integration by parts. How are you using integration by parts? Oh yeah, no, that's fine. So then we take the limit of this. There we go, we're fine. We take the limit of this as a approaches 3. Now what we're going to say is we are limiting, this is where you might, the 3 that you were saying, right? We are approaching 3 from below. So 3 minus. A is getting close to 3, but is less than 3. So you might see something like this with a minus as a little exponent or a positive, but then this becomes minus 0 minus 3, which is 3. I was bugging, boys and girls. I was taking A going to 0. I was absolutely bugging. So our integral comes in at 3. So Mohammed, you can, but it won't come out nice, right? Because your 1 over square root 9 minus x squared will give you an arc sine, but when you do your integration by parts, the integral you're left with will not be integrable, right? The trigs, I mean, oh crikey, like if you really want to, right, you possibly could go for a trig sub x equals 3 sine u if you really wanted to. If you really wanted to, you could possibly make that one, but your limits are going to be awful. All right, your limits will be awful. Okay. Yeah, but so the a value, if you just do it from 0 to 3, you just have to be real careful because 3 is undefined. All right, 3 is undefined. I won't lie to you. I probably, if I was doing this myself, I probably wouldn't worry about the 3. All right, I probably wouldn't worry about the 3. All right, and C is very much the same thing, 0 to infinity x over square root 1 plus x squared. All right, why? Because infinity is undefined. That's awful for me. But here's another nice little trick that we could do for this one. Well, actually, no, let's not worry about that. But again, same sort of trickery here. All right, infinity is a problem. Are there any holes in the function? No, x over square root 1 plus x squared is not a problem. And if you're not sure, right, whether it's you're at home, just do a quick sketch, but you're absolutely fine. This bad boy here, it has an asymptote at 1. It's very, very nice. All right, so we're going to multiply and divide by 2. And what we're going to do is we are going to integrate up to a. All right, very much the same thing. This just becomes overall square root 1 plus x squared between 0 and a, which becomes square root 1 plus a squared minus 1. But then if you take the limit as a goes to really, really big, this becomes really, really big, which is also undefined. Boys and girls, if you want to know how I went from here to here, just do this substitution. You are recognizing a function and its integral, right? You are realizing that it's an inverse chain rule. That is f dashed of x. That is f of x. Like I've said before, there is enough going on in further maths core pure that your integration needs to be on point. All right, absolutely on point. But that's what we're doing. So this diverges in C. This is a divergent, undefined diverges. Okay, but by and large, you can make the u equals 9 minus x squared substitution in part B, right? And this is why I multiplied and divided by minus 2. Same thing here, by the way, if you aren't seeing that. And you can make, or you can make the substitution u equals 9 minus x squared. Black ninjas twigged. There we go. Right, it is time for us to have a little break. I think our brains are overheating a little bit. So it is 11:37. It is 11:37. So we are going to come back at 11:50. We will come back at 11:50. I'm going to give you 10 minutes just above to have a breather. What I'm going to do is I am going to leave up for this one, I'm going to leave up our little link for any of you that are not yet signed up to the full Easter revision. All right, for all the modules coming up tomorrow, the day after. So we've got stats tomorrow, further mech on Friday, D1 on, nope, FP1 on Saturday, and D1, FP1 on Saturday and D1 on Sunday. So it goes stats, mech, FPD. I think I've put them in the order of the exams, possibly. But that's coming up this week. So if you want to sign up for those, get all the recordings, the video solutions for all the papers, just check out the link from the QR code. So 11:50, we will come back. So I'm going to give you a 10-minute breather now, just above, and then we'll do 20 minutes for lunch around about just before 1 o'clock. And then we will go all the way to the end, boys and girls. Right. Peace out. Wob, 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 wob. We're back. We are back, everyone. We're going to go straight in. No mucking about. Let's go on to matrices. Now, matrix multiplication. Super simple. No, it's not. But adding matrices, we're not going to talk about. That's super, super simple. But things to realize that, of course, it is non-commutative. It is non-commutative. So we know how to do this. We are well cool. 1 minus 2 minus 1, 3, 0, 1 times by 1 minus 2, 0, 0, 1, 3. We have to look at the rows and the columns. Now this matrix here, A, is a 2 by 3, 2 rows, 3 columns. Matrix B is 3 rows, 2 columns. The important thing is that these bits match. That is the important thing. That is, we need to match. And what we need to do is we are going to basically go along a row of the first matrix and down a column of the second one. CG50 can do it for you, but ain't gonna lie, it does take a while. So 1 times 1 plus minus 1 times minus 2 plus 0 times 0. I'm not going to do it for all of them. Okay. I literally, if you ever see me doing this live, I will be using my fingers to go along rows and down columns. All right. There's not a lot I can do about it. Minus 2 times 1 is minus 2. 3 times minus 2 is minus 6. 1 times 0 is 0. So first row, first column, you get the rows from the first one, columns from the second one. If I want second row, first column, second row, first column will give me that one. And so on and so forth. It is fiddly to do on the computer, I won't lie. 0, I think that comes out as a 6 if we do that. So this should come out as 3 minus 8 minus 1, 6. Can I get a check on that? Good. Now we can do b times a in this case, which is kind of nice. If we do b times a, let's just double check. It's going to be a lot bigger. 1, 0, minus 2, 1, 0, 3 times by 1 minus 2 minus 1, 3, 0, 1. And again, if you look at this, this is 3 rows, 2 columns. And this is 2 rows, 3 columns. The important thing for this to work is that these two work out. And this is going to be a 3 by 3. So if I want the first row, first column, I basically multiply and add these terms. 1 times 1, 0 times minus 2. We could then go the second column. And I'm not exaggerating when I tell you I struggle doing this without being able to follow it with my fingers to make sure that I am getting the right terms every time. Oh, someone ran away. So that one's a 0. Okay. So I think that's a minus 4. Minus 2 times 1, 1 times minus 2. Minus 2 times minus 1 is 2. That's a 5. That's a 1. If I don't make a mistake doing this, it will be an absolute miracle. 0 times 1, 3 times minus 2 is minus 6. 0 times minus 1 is 0. 3 times 3 is 9. 3, 0. Right. Oh, I get the same thing as Mohammed, right? So nice and straightforward. The other thing I want to draw your attention to is that the dimensions of the resultant matrix are given by these leftovers. All right. They are given by these leftovers. A squared, 1 minus 2 minus 1, 3, 0, 1 times by 1 minus 2 minus 1, 3, 0, 1. This is impossible, because this is 2 rows, 3 columns. This is 2 rows, 3 columns. And if you have a look at these two, we have a big, horrible, they don't match. It is impossible. It is impossible. Okay, impossible. That is a mismatch. It does not work. Did not match on Hinge. Guy does matrices ridiculously fast. It does it easy quick. Right. Now, determinants. Determinant of a 2 by 2, nice and simple. Nice and simple, the determinant of a 2 by 2. All right, A times D minus B times C. The intricate reasons why this is a determinant, why it does what it does, is not for us to worry about. Okay, so we will use modulus. There is a sense, right, of the idea of size of a matrix with a determinant. So this idea of a modulus, okay, so you will often see me use a modulus sign for it like that. 3 times 1 minus 3 times minus 2. So I make it to be 9. All right. And you could be asked to do it with one which has algebra in it. So 2 plus a 3, 8 minus a 2. That determinant is 0. So if we do that, it's like a nice little cross. That is 4 plus 2a minus 24 plus 3a. Nice and simple. 5a is, oh, we're in blue. I make a to be equal to 4. Right. Now the bad one. The determinant of a 3 by 3. This one is nasty as well because I've made it so that not a single one is 0. You pick a row, you pick a column. We're going to pick a row. I just normally just pick the first row or the first column. It doesn't matter. Now, we're going to whack in our cheeky plus or minus. Now, this happens a lot when we're doing stuff with 3 by 3s. This sort of plus minus grid gets superimposed on it. It is what it is. Right, what do? We take one of it. Oh, dear. We're going to take the first element there. And what we do is we cross out what's left. So what I need is I need plus 1 times, and we're going to take the determinant of what's left. 3 minus 1 minus 4, 2. Don't worry about the pluses or minus. They just work for this first term. And then what we do is we take the next one and we cross out the row and column that that term is in. So that one did pick up the minus 2, the minus. And we take the determinant of what's left. So minus 1, 2, and 2. And then we move it along, next term in the row, plus minus 2, that is a minus 2. We cross out what was left, and we're left with minus 1, 3, 2, minus 4. Okay? And that's what we need to do. Your calculator can do it. This is the minors. So these are the minors. Okay, so these are the minors, the minor matrices for each term, and so on and so forth. I really don't remember all the names, okay? Why? I just use them. So now we do this determinant. 3 times 2 is 6, minus 4 is 2. This one here, minus 2 minus minus 2 is 0. Ooh, oh yeah, it's repeated. Very nice. This one here, 4 minus 6 is minus 2. So I make this to have a determinant of 6. Boosh! Love it. Okay, now if you were so inclined, you could do this plan along any row, any column, right? You can do this along any row, any column. Not a problem. You can absolutely do it along any row, any column. You should come out as 6 no matter what. So generally try and look for one that has zeros in it. Try and find ones that has zeros in it. What do you mean, Mohammed? What is capital A2? You sunk my battleship? Inverses. Oh, right. Right. Inverse of a 2 by 2, we just need to remember. Here it is. Inverse of a 2 by 2. All right? Inverse of a 2 by 2. So we just need to do it. So for number A, the inverse of A is 1 over the determinant, 4, so that's 1 over 14. And then you're going to swap the main diagonal and then take negatives of the other one. Now, what does this actually tell me? Why is this the inverse? Well, if I do A minus 1 times A, what do I get? I get 1/14. And you can check this, right? Uh, 1 times 4, 2 times 5 is a 14. 0, 0, 14, which is 1, 0, 0, 1. This is our identity. This is our identity matrix. And the idea behind it is that 1, 0, 0, 1 is basically the equivalent of 1, right? If you multiply a matrix by this matrix, you will just get the original matrix. Is basically 1. It is our identity. Okay, so that is how this works. Now, why might this work for B? How might I find B? Well, if AB is equal to 8, 3 minus 6, 3, 6, 4, if I multiply this by A minus 1, now what becomes very important with matrices, because as we saw in the previous slide, which way round you multiply is very important. So which side we multiply by is very important. So if I multiply by A minus 1 this way, the A and the A minus 1 cancel. But it is important to do it from the correct side. Silly boy. Okay? So 1/14 of 8 plus 6 is 14. Minus 6 plus 6 is 0. 6 plus 8 is 14. Oh, this is cool. Minus 40 plus 12 is minus 28. 30 plus 12 is 42. And minus 30 plus 16 is minus 14. And of course, if I multiply a matrix by a number or divide a matrix by a number, it's every single number needs to get multiplied by that. So hopefully this is what we get. And I need a lot of space for part B. Any thoughts on this so far, my lovelies? Okay. All right. Now the next bit. Hopefully we're okay. Lost the chat. Easy queasy. Cofactor matrix. All right. So unfortunately, what they like to do is make you do this sort of thing with matrices with unknowns for a 3 by 3. So what we need to do. So we're going to need to find the determinant. Yes, we are. There's a whole bunch of stuff that we're going to need to do. So we're going to need det of A. So what is the determinant for A? I'm going to go along this row. I'm going to go along this row. So it's 2 times 4 minus 2 is 2 times 2. The nice thing with this row is that one won't give me anything. So we're here plus 3 times k minus 1. So I make that 3k plus 1 as the determinant. Right, there's a whole bunch of steps that you can do in multiple orders, okay? That's 3k plus 1, right? I do believe. Four minus 1 is 2. Ah, yeah, 2 times 3. Yeah. Thank you. So 3k plus 3. That actually feels a little bit better. 3k plus 3. Right. Now for the really annoying thing. I'm going to make this big. We are going to do this similar idea with these minors for every single term. So for this first one, we're going to take the determinant of the minor that goes there. We're then going to put in the determinant of the minor that goes here. And so on and so forth. The determinant of the minor at the top right. I won't lie, it's going to start getting tricky for me if I don't actually start annotating this. Ah, this one's not too bad. Right. So, Liam, there are multiple steps we need to do. So you can do it in any order. We are going to do 3 things, well, 4 things. The determinant, we've done it. The minors, we're going to do it. We're going to need to transpose this and then the plus or minus. So there's a whole lot that we need to do here. All right, so let's finish this step, but you can do them in any order, right? You could put the minus pluses in now, you could transpose it now, you can do these at that point, right? It doesn't actually matter. You can do that at any point, but let's figure this one out. So 4 minus 1, almost did the same thing again. 4 minus 1 is 3. 4k minus 1, k minus 1, and then here, minus 3, and then 5, and then 2. Hop in if I make a mistake. Minus 3, 2 minus 3k, and then 2. The middle right. 2011, is it? It is 2011, see? Thank you. Still comes out as 2 though. Right. So that's step 1. We are then going to put in my plus minuses. I'm going to put in my plus minuses. And then I'm going to transpose it. Last step, we transpose this. So the main diagonal stays the same, which is not quite nice. I quite like that. So 3 minus 3 plus 3. So we found all of those little determinants. Ah, I have. Ah, Rootchit, why are you doing this to me now? Why are you doing this to me now? I did muck it up. Ah, there we go. Ah, I hate you a little bit right now. You could have left me in blissful ignorance. Right, let's check these signs. 3 plus 5 plus 2. So that's a 3, that's a minus 3. Ugh. So that's still a 1 minus 4k, that's still a k minus 1. 3, 5, that's a minus 2. Minus 3, that should be a 3k minus 2. And then that should be a plus 2. And then finally, our determinant. Oh, it's just alternating, right? For these plus minuses, you start with a plus and then you alternate minus, plus, minus, plus, plus, minus, minus, plus. You just alternate. That's all it is. But of course, if you're distracted and you get it wonky, then it goes wonky. Okay. But these are the 4 steps. Determinant, the determinants of all the minors, pluses or minuses, the transpose. By and large, you can do it in any order. By and large. Find one that works for you. Just do the determinant first. Pretty much this is the order I go in. I find all of my little matrices, then I do the plus minuses, then I transpose. Up to you, really. But this is horrific. And if you really have time, if you really have time at the end, you could try multiplying these 2 matrices and making sure you get the correct thing. Check the third one on the second row. What, the 3k minus 2? Or here, the minus 2? Which one? At what point? Transposing, Liam, is you just swap the rows and the columns. So the transpose is basically you're swapping the rows and the columns. Is the inverse of the inverse the original? Yes, it will be. It will be. And if you want to go through that whole process here, you will see that that works. Right, now, why could this be useful? Why could this be useful? Because systems of equations, you can write as a matrix. You can write in matrix form. Okay? You can do it in matrix form. So what I can do is if I can find the inverse of this matrix, I am golden. And I will quickly take the time to show you how to do that. So this will be largely the same for CG100. I've had a little play. we're going to go into matrix mode, and I want to play around with a 3x3. So this one is 1, 1, minus 1, 2, minus 1, 1, minus 3, 2, minus 2. So we have now saved that as matrix A, which is kind of nice. Because what I can do now is if I go into my matrix mode here, matrix A, and in theory, if I go to the power of minus 1, okay, do I need brackets? Do I need brackets? It has no inverse? Is that so? It has no inverse, this one. Well, that's a whoopsie. Oh yeah, because it's going math error. Bottoms. All right, let's change it. Change one of these numbers. Should we change it to 2x on the first row? Let's change it to 2x. Huh, that should not have slipped through. Let's change the first one to a 2. Still math error? No. Why would that be a math error with a 2? Surely not. What have I managed to make here? What? How unlucky am I that this has happened? Hang on. How unlucky am I? What the actual fiddlies? Change the middle top to a 2. All right, let's change that to a 2y. Let's do that. The matrix itself is completely by the by. This is what happens when Nick tries to put something together, but there we go. That's good enough. There we go. All right, so that is my inverse, 0 to 1, 1 minus 5 minus 3. Thank you, whoever spotted that that would work. No idea how unlucky I got there. But what I can then do is I can then say, same idea as before, x, y, z is this inverse matrix times my vector, and off we go. So 0 times 0, 2 times minus 3 is minus 6, plus 5 is a minus 1. 1 times 0, 15 minus 15 is a 0. 24. So does that work? 2 minus 1, 3. Yeah, that works. Cool. So that tells me that x is negative 1, y is 0, z is minus 1. And I'm not sure, but I'm fairly confident this is how your calculator does the simultaneous equation solver. Okay, that's largely how it does it. Gulp. Cool. Let's keep moving. We motor. All right, matrices and transformations. Matrices and transformations. So basically, what matrix takes me from xy to 2x plus y, x minus y? It is this matrix, 2, 1, 1, minus 1. Okay, very, very easy. Why? Because if you multiply that by xy, you will get 2x plus y, x minus y. So this matrix is a transformation, right? It represents a 2D transformation. Nice and simple, all right? And we can use this to transform points. So if I want to transform the point minus 1, 2 under this, all I do is minus 1, 1, 3, 2 times by minus 1, 2. Nice and simple. So 1 times minus 1, 3 times 2 is a 5. Minus 1 times 1, 2 times 2 is a 5. And there we go. So minus 1, 2, the point minus 1, 2 gets mapped to 5, 5. All right, some great stuff in the chat. Yes, if the matrix doesn't have any letters in it, you can just use your calculator to find the determinants as well. Nice and simples. All right, but largely when they ask you for the determinants of a 3 by 3 or the inverse of a 3 by 3, they're going to put algebra in it because they know that most people are using these types of calculators now. All right. Now, what you do need to be able to do is figure out the matrix corresponding to a transformation. Now, who can put in the chat, what's the nicest way to figure out the matrix corresponding to a transformation? What's the best way to do it? 1, 0, and 0, 1, the unit square. Good. We're going to look at where the unit square goes. So a reflection in the line y equals x. I'm actually going to do this. All right, I'm going to do it step by step. I'm going to do this step by step. So let's find the matrix corresponding to a reflection in the line y equals x. So I'm going to look at where the point 1, 0 goes to. Well, it gets reflected to 0, 1. All right. So my reflection in, so the reflection, the first bit will be 0, 1. And then the 0.10 gets reflected back, right? They get reflected to each other. So 1, 0 goes, sorry, 0, 1 goes back to 1, 0. Okay, so we are looking at columns. Okay, if you think of it as position vectors, 1, 0 gets mapped to 0, 1, 0, 1 gets mapped to 1, 0, and that's how I populate my matrix. How about the rotation? How about the rotation though? So it does have sines and causes. It does have sines and causes. So let's start with 1, 0. Let's start with, oh dear. Let's start with 1, 0. Stop it. Thank you. Okay, let's start with 1, 0. That is length 1. We have rotated it 30 degrees. Where has it ended up? That's far too thick. Well, a little bit of trig will tell me that that has gone to the coordinates cos 30, sine 30. And in the same way, if you have a look at where 0, 1 has gone to, that is length 1, its new position vector will be at minus sine 30 and cos 30. Basic SOT Katoa. Hang on, need to rescale that. Okay, so the rotation, if we have a look at that, by d, yeah, I've done anti-clockwise. We want clockwise. Ugh. All right. So what's the only difference if I go anti-clockwise? Not a huge number of differences if I go anti-clockwise. RTQ, Nick. RTQ. Who rotates clockwise anyway? Honestly, who throws a shoe? Okay, so this one has been mapped to cos 30 minus sine 30, and this one has been mapped to sine 30 cos 30. There we go. I use drawboard, which if you're with Dav, he tends to use as well. Okay, so my rotation there, you look at where the 1, 0 goes, which goes to cos 30, and then minus sine 30. And then the 0, 1 goes to sine 30, cos 30. Okay. Now, which order do we do them in? We're going to go right to left. So you do the reflection first. So we can do the reflection first. Actually, I need a bit more space. So I need to do the reflection first, followed by my rotation. Now, cos 30 is root 3 over 2 minus a half, root 3 over 2. So the overall matrix is That should be it. Okay. Now, gloriously, if I remember correctly, I just need to find it. Aha. Ah, come on. That is in the formula booklet for you. Okay. But the default for the formula book is anti-clockwise. All right, is it anti-clockwise? Now, like someone said, you can formulate it. 30 degrees clockwise is 330 anti-clockwise if you really want to, but this is what it comes out from. That is for the reflection in the line y equals tan theta. It is there for you for that. Okay, but it is fairly straightforward to get most of these. I tend to do it from scratch. So go, why are the angles not negative? Well, I've done mine from scratch, right? So you'll see mine is cos, sine, sine, cos, right? So because it's anti-clockwise, if you compare what I got to what they've got here, you'll notice their signs on the signs are the other way around. They've got the minus at the top right and the positive at the bottom, which is also what will happen if you put in minus theta for going clockwise. All right, if you compare it to mine. But again, this is one of those ones as I tend not to remember it. I tend to just do it from scratch. Right. But you need to be able to do this. But remember, the key thing is the order of operations. We work our way from right to left. We work right from left. So first, the very second one goes there. Now, reflections in 3D. So you can do the exact same thing. You can do the exact same idea. You just have to look at where your unit vectors go to. Where does 1, 0, 0 go to? Where does 0, 1, 0 go to? Where does 0, 0, 1 go to? Now, in 3D, you reflect through the plane. So this is the plane, x is 0. So if you reflect in the plane, the only vector that gets reflected when you reflect in x is 0 is the vector 1, 0, 0. And that gets shot off backwards. So that one will become minus 1, 0, 0. The other ones don't move. This bad boy here is the plane y equals 0. The only vector that gets shifted around in this case, the only vector that gets shifted around in this case would be the vector 0, 1, 0. That is the one that's going to get pinged onto the other side. And this bad boy here in Z is 0. The only one that is going to get pinged is 0, 0, 1, which gets reflected down here. And there we go. Keep on target, boys and girls. We're going to take a break in 15 minutes. Now, 3D rotations is a little bit trickier, but it's actually okay. Now, this one, so that's AS Further Maths formula sheet. Okay. Did they not put it in here? I thought, top of my head, it was in here. Is it not? Interesting. Okay. Rotation 3D is just weird. Now, first of all, you pick an axis to rotate around. So we're going to pick an axis to rotate around. Okay. Now, the best way to visualize this is to start yourself with the z-axis. Now, picture yourself looking down at this from where z is. So you're looking down at the xy plane. So if I'm rotating around the z-axis, I'm going to keep that z1 absolutely identical. All right? Where that 1 is, I'm going to keep it absolutely identical. The rest of it, right? The rest of it is the rotation matrix cos theta for a 2D. Right? Rotating theta degrees this way, clockwise. So when you're rotating these things, so this is why I like Z. Picture the axis you're rotating around pointing out at you, and then you're going to rotate, right? Then you put the other ones as if they were the X and Y, so going to the left and going up. Then you're going to rotate anti-clockwise that way. So if you want to do it around the x-axis, right? If you want to then rotate around the x-axis, what would we do? I would keep the x-axis identical, all right? So now we are rotating around the x-axis. Now, again, have that x-axis pointing out at you. So basically, we are here, right? We are looking at this way from here, okay? Along the x-axis, down the x-axis. And what we'll do is we will start rotating that way, and we are going to put in our cos theta. Sorry. There we go. And we're going to put in our cos theta minus sine theta, cos theta. Okay. I was fairly sure it was in here as well, but for some reason it's not popping up. Edexcel, I was fairly sure the 3D ones were in here as well, but I have lost them somehow. Are they under the A2 or AS? So we got the 2x2s. And then we're into stats. Edexcel it isn't. So you do need to know these ones. All right. And if you want to rotate, that's why you had me confused. And if you want to rotate around the z-axis, so this is around x. Sorry, if you want to rotate around the y-axis, you will keep the y bit absolutely the same. And then we're going to fill in all our other bits. Cos theta minus sine theta, cos theta. Okay, and what that looks like is we are now looking at it. Oh, no, we are now looking at it down here. We're looking down the y-axis. I think we'll be rotating that way, theta. So the sine theta, it depends how you're defining clockwise and anti-clockwise. It depends how you are formulating clockwise, anti-clockwise. Okay. It really does depend, yeah, how you are defining your clockwise, anti-clockwise. But yeah, that's pretty much how it goes. But that's one that you need to know. That's just one you need to know. Right, 1234. How are we doing? So we've got the scalar product to do, and then all of our vectors. I think that's it. Okay. So let's quickly introduce the dot product. Now, before we go into all of our vectors and all of this, yeah, before we do all the vectors and so we're going to be talking about distances in 3D equations. Very importantly, I'm not going to use the cross product. Now, I know most people, including myself, will just teach the cross product, and then you can use the cross product to find all the distances. I might refer back to it. I'm going to refer back to it. Can I get a quick plus minus in the chat, or just anyone in the chat that has not learned the cross product? Put a minus in the chat if you have not learned the cross product. Okay. So the cross product is further pure. It's FP. It's FP1, the cross product. It is super duper useful for doing 3D geometry, and you are allowed to use it. I'm going to try and do as many questions as I can without the cross product, apart from one thing today, which is we are going to use the cross product to find perpendicular vectors. Okay. So Ishan, the signs depends very much how you're defining the clockwise, anti-clockwise. It's because the minus can come from the orientation of the X and Z axes. That's why. Okay. However you've learnt it, whichever formula you have written down and you have learnt, and whichever orientation you are most comfortable with, you go with that. All right. That's all I'm going to say. So you go with whichever orientation you are comfortable with for your pluses and minuses. Okay. That's important. Okay. So scalar product, dot product should all be in AQA. Tell you what, before we embark on this, so I can give you a bit more of a breakdown, because I do have this. Breakdown, breakdown, breakdown. Bum, 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 bum. Right, referring back to my spreadsheet here. Pure matrices, vectors, vectors, vectors. Ah, so in fact, this is one of these rare areas where it doesn't quite line up. So if you are doing AQA, the rest of what we're doing today, as far as I can tell from my spec breakdown, doesn't apply to you. All right, it doesn't apply to you. The vector product, if you do OCR in any way, shape, or form, the vector product or the cross product is part of your core pure. So this is one of those topics that doesn't line up perfectly across the specs. So if you're doing AQA, the last bit of today isn't for your exam board. And then there's a couple of bits and bobs that won't quite line up between Edexcel and the two OCRs, OCR A, OCR B. But I'm just going to cover as much as I can. And yeah, that's the plan here. Okay. You sure? My AQA here. Are you sure? Because when I went through the AQA spec, vectors did not come up. But I haven't looked at this in a while. AQA further maths spec. AQA A level. I mean, don't get me wrong. I was looking at all four specs at the same time. So if I missed one, I missed one. But subjects maths, AS, A level further maths. Let's have a quick look. Subject content, compulsory content, complex numbers, matrices, 2x2s, 3x3s, simultaneous. Oh, you do eigenvalues and eigenvectors. That's cool. Inverse. Huh. No, vectors are in it. Ignore that. All the vector stuff is in for AQA. Somehow I missed that in my spreadsheet. Cool. Wicked. Thanks for that. I'll need to check that. So ignore that. This last bit is for everyone. Thanks for that. I need to change my spreadsheet. Missed an entire topic for AQA. Sorry, AQA. I won't lie though. Those of you doing AQA, it is mental the quantity you do. These short, like especially in the applied modules, it is super wide what you do in stats and in mechanics. It is absolutely mental, which is probably why I was like, yeah, that's chill. They don't do vectors. Yeah, absolutely bonkers how much goes into there. Yeah, you've got most of further pure in just your normal core pure. It's absolutely redonks. Yeah, so sorry about that little misunderstanding there. Okay, so it's 12:40. Just to keep the time rolling adequately, what we're going to do is we are going to break now. We're going to break for lunch now for 20 minutes. All right, so 20 minutes now, 12:40 till 1 o'clock. And then we will push through until we finish after that. Okay, so we are going to come back in 20 minutes. I'm going to put up for you there we go, our little link. If you are interested in hanging out and doing exam prep with me between now and your exams, basically for each and every paper, this is very so I know a lot of you are on here doing AQA and the OCRs. As soon as we get onto the applied modules, we are very much catering towards Edexcel. I am yet to find a way to do all of the applieds, the topics for every single exam boards, because as soon as you get into further mech, further stats, anything like that, it is the absolute wild west of content. So we are very much catering to Edexcel for the exam revision, the exam masterclasses, and for the applied modules this week. So be aware, please. The exam masterclasses are in 2 parts for each exam. One lesson 2 to 3 weeks before the exam, where we go through big topics. And for all of this, it is very much not like this, where we're like high level. We are going into exam questions, how to do the fiddly bits. We'll be looking at some mark schemes as well. And then the night before, you get your cram session, 4 to 5 hours, the night before the exam, where we just smash through a load of stuff. And you get your revision guide in between, which goes through the spec breakdown, again for Edexcel, with the links to past papers, to video solutions, to all the good stuff. Okay? So the mechanics session is FM1. It's Edexcel FM1, Edexcel FS1, Edexcel FP1, Edexcel D1 for the rest of this week. All right, so that's our breakdown for the masterclass. So say you are doing Edexcel and further maths, and you've got further mech as one of your options. I think it's 3 weeks before the further mech. We have an evening session where we go through for 2 hours. We'll basically go through a paper, highlighting a paper where I've cherry picked some of the harder questions I can find, highlighting all the things to look out for, all the techniques, where the marks come from. We'll go through all of that. Then you get your revision workbook, which will have the further mech formula you need to know, all the big ideas, references from the spec to exam questions from Edexcel past papers. We won't include the papers themselves because we don't work for Edexcel, as well as links to my own questions and solutions that I have done that are available online that you can go check for each topic. And then the night before the further mech, you will have a 4 to 5 hour session with me, again going through some more exam questions and some bit of time for Q&A. So that's how the masterclass would work. And if you sign up for it, we'll do that. And say you're doing further mech and further stats, you will do that for Core Pure. So you'll get 2 cram sessions and a pre-session for Core Pure, and you'll get a pre-session cram session for further mech and a pre-session and a cram session for further stats. So if you follow the link that is up right now and just scan the QR code up there, that will take you through to the registration for it. Okay, right. Having said that, that's 4 minutes of our lunch break. We will come back at 1 o'clock to finish this off. See you in a bit. Ooh. Ooh. It's time. It's time to do some vectors. Oh, time to get the pen to work. Is it going to work? Yes, pen is on. Lovely. Hopefully we are back. We are ready. We are ready to rock and roll for our last little sprint here. Right. Final stretch. Scalar product, the dot product. So here's our definition up here. We're going to use it quite a bit. But basically, -1, 2, 3, if we do the dot product or the scalar product, depending on what you prefer to call it. It's called the scalar product because it gives us a scalar, a number, a singular number. It's called the dot product because we use a dot, because there's two different ways to multiply vectors. So we do the first terms multiplied together, the second terms multiplied together, the third times multiplied together. -1 times 1, 2 times 0, 3 times 1, and we add them to get 2. That is our scalar product. However, it can be shown, not by me, not right now, but it is also equivalent to the modulus of A dotted with the times the modulus of B times cos theta. So you have to think of it this way, right? If I've got a vector A and a vector B, you've got the length of vector A, you've got the length of vector B, and there is an angle in between them. So this dot product here, this 2, is also equal to mod A, mod B, times cos of the angle between them. So the modulus of A is just Pythagoras, that's square root of 1 plus 4 plus 9. Modulus of B is square root of 1 plus 1 cos theta, so that is 2 is root 14 root 2. So cos theta, I think, is root 7 over 7. Cos theta is square root 7 over 7. And then we just need to find the acute angle. So we're going to go, make sure I'm in radians, shift cos of root 7 over 7 to get theta equals 1.18 radians. Okay, so the acute angle. Really, it doesn't matter if you use degrees or radians. Just read the question, right? You could also do it in degrees. I tend to stay in radians for as much as possible so that I don't have to then muck about with it. But yeah, we can do it in degrees if you want. Whichever one you're in, if the question doesn't specify which unit to use, choose whichever one you are happy with, but make sure you put the units. Okay? So 1.18, I put the little c for circular measure for radians, just to make absolutely crystal clear that I'm in radians. If the question says in degrees, work in degrees. If it's a part C and parts A and B have been in degrees, work in degrees. In a vacuum, I default to radians. Why? Because so much of the papers, so many of the questions involve integration and differentiation. I just prefer to keep everything in radians, but that's me. Mechanics, I will shift over to degrees pretty much all the time though. But that's it. That's our idea. Okay, so that is the scalar product. I will refer to it a lot as the dot product because you can't stop me. You're not my real mum. So I'm going to do that. Now, equation of a line. So let's find the equation of a line that passes through the point 1, 0, minus 1. So it goes through the point 1, 0, minus 1, and it goes through the point -2, 3, -4. So there's a bunch of stuff we are going to do. What color should I use for my line? Let's use blue. Blue's a good line color, isn't it? Yeah, Nick, it sure is. Yeah, I thought so. I thought you'd agree with me. So the first thing we're going to do is we're going to find a direction vector for this bad boy. So I just find the vector that goes from one point to the other one. So how do you get from 1 to -2? That's -3. From 0 to 3, that's a 3. From -1 to -4, that's a -3. Now, there is absolutely nothing stopping you at all, absolutely nothing stopping you from instead using, once you've got that one, if you prefer smaller numbers, you could also just use -1, 1, -1. That is also absolutely fine. No problems there. But the point is, we need a direction vector. Now, what do we do then for our equation of our line? Well, any point on this line, which has position vector r, which is x, y, z, by the way. So how would you get to any point on the line? Well, let's start somewhere on the line. I'm going to start at 1, 0, -1. It could be at -2, 3, -4. That's it. Meh. And then we're going to add on some amount of our direction vector. And you know what? I will use the -1, 1, -1. It doesn't matter. Okay. And depending on where you are on the line, so here at this point, oh, actually, let's use here. So here I would have lambda is 3 would get me to that point there. Here, if I went lambda is -1, I would be at the point, we would be going that way for 1, -1, 1, right? And so on and so forth. It really, depending on how you choose lambdas, I might take lambda as 6 and end up all the way there, which will be -5, 6, -7. Another lot of that direction, another 3 of these -1, 1, -1s, right? That is what we've got going on. So really, the equation of a line in 3D is all about a starting point, and then you're going to add on multiples of a vector to go up and down your line. Let's get that into Cartesian form. Well, if we split this up into its components, and we make lambda the subject. So the first one tells me that lambda is x -1 over -1. Lambda is y. The third one tells me lambda is z -1 over -1. Put that together because they are all equal to lambda. I'm actually going to write the y one in a particular way, because the nice thing about it is, oh, that's z plus 1, isn't it? But you know what? I'll tell you why that is. Z equals, and what I'm going to do is I'm going to write that z plus 1 as z minus -1. There we go. And you can see the point on the line by having it that way, and you can see your direction vectors here. You can see your direction vectors. You don't have to simplify that at all, historian. No, I could have done all of this with -3, 3, -3. It is absolutely legitimately fine. I do tend to simplify my direction vectors. If there's an obvious one, they're all multiples of 3, I will tend to scale it down because later on in questions, it might make my life a little bit nicer. That's all. Okay? So this is vector form. This is Cartesian. So the Cartesian form for a line does have 3 parts to it. It does have 3 parts to it. Does it matter which point you use for the direction vector? Well, you will normally have 2 points on a line. So here I was given these 2 points on a line. I didn't really have a choice. Those are the only ones to find my direction vector. What you can do though is I used 1, 0, -1 for my point on the line. You could absolutely have used -2, 3, -4. That was not a problem. You absolutely, completely, totally could have used that one. Okay? So there are choices for you here. It is not unique. It makes it annoying to mark, because you have to check everyone's points. You have to check everyone's direction vectors. Okay. This is the equation of a plane. So this here is the equation of a line. No slurp. I turned it off. You can't say that. I turned off the microphone. Right. Equation of a plane. So in general, what do we do? The equation of a plane comes from one simple fact. If we have a vector that is, well, that is just a shocking little vector there. If we have a vector n that is perpendicular to the plane. All right. The idea is this, is if you take a point on the plane, so we know there's a point A on the plane. So we're going to take a different point, X, Y, Z on the plane. We know that the vector from A to R is perpendicular to N. Now, an important point that we didn't really talk about with the scalar product is this. If A and B are perpendicular, i.e. theta equals pi over 2, then looking at this, that will tell me that A dotted with B is equal to 0. Kind of important. So the idea of the equation of a plane is to say that the vector between R and A has to be perpendicular to that normal vector. So this is the idea behind the equation of a plane, and if we multiply that out, you get R dotted with N is equal to that point dotted with N, and we normally just call that, whatever that is, just a constant. Okay? So, here's the trick. I've got 3 points on my plane. I've got the point 1, 0, minus 1. I've got the point minus 2, 3, minus 4. And I've got the point 0, 1, 2. What we need... Now, there is a bunch of ways we can do this, but we just use the dot product. I won't lie to you. The scalar product, the cross product, and I can do it, right? We want a vector that is perpendicular to both of these. We want a vector that is perpendicular to both of these. The easiest way to do that is with the cross product, I'm afraid. It is. So the first thing we're going to do is we're going to find the vector that goes from these points. So 1 to minus 2 is minus 3. 0 to 3 is 3. Minus 1 to minus 4 is minus 3. 1 to 0 is minus 1. 0 to 1 is 1. Minus 1 to 2 is 3. Now again, minus 3, we could absolutely use instead minus 1, 1, minus 1. Absolutely we could. Right. Now we need a vector that is perpendicular to both of these. Two options. Two options are available to you. All right. You could say that the normal vector is ABC, and then you're going to go ABC dotted with minus 1, 1, minus 1 is 0. So you get minus A plus B minus C is 0. And the vector dotted with minus 1, 1, 3 is equal to 0. So minus A plus B plus 3C is 0. And you could try and solve this. Now, this always has a degree of freedom to it. Here's a nice little trick for you. It always has one degree of freedom to it because the vector can be as long and short as you want. So say you could pick, never pick 0, but you could pick C as 1. So equation 1 becomes minus A plus B is equal to 1. And equation 2 becomes minus A plus B is equal to minus 3. There is a problem here. Okay, there is a problem there because that is obviously impossible. So that does actually tell me something. This tells me that C needs to be 0. Now, the reason I'm showing you this is that this is not necessarily straightforward. This is not necessarily straightforward, right? You need to have a little, it's because you've got minus A plus B minus A plus B. Now, for me, I can see straight away that C has to be 0 and then A has to be equal to B. So I would take 1, 1, 0 as my normal vector. Okay, but that requires a little bit of thought and so on and so forth. So instead, what we're going to do is we are going to take the cross product. If you don't know what the cross product is, I recommend you look it up. It's in, if you're doing Edexcel, it's in FP1. Otherwise, all the other ones know about it. So we're going to do the cross product. It's just a bunch of matrices. So that will be 3 minus minus 2, which is 4. 1 minus minus 3, 4. Minus 1 minus minus 1 is 0. And you'll notice these are in the same direction. They are multiples of each other. So it's, Shruti, if you say C is 1, you will get contradiction, so it won't work. The only way you can get C as 1 is with A and B equal to 0. All right, and that won't work either. So what you really want is actually, low-key, you need C as 0. So this is the first equation of a plane. All right, so the equation of our plane is going to be r dotted with 1, 1, 0 is equal to some constant. Now, to find the constant, just take any point on the plane. So I'm going to take, I don't know, this point on the plane. You could take that point on the plane. You could take that point on the plane. It doesn't matter. And dot that with 1, 1, 0. So I get r dotted with 1, 1, 0 is equal to 1. So the cross product, for those of you, you'll notice I don't use IJK notation. The cross product is the determinant of vector, vector, IJK. And if you then work your way down here, you should get what I got. You should get what I got. Now remember, R is X, Y, Z. So that is X plus Y plus 0, Z. So you could just leave it as 0 is equal to 1. So it's just X plus Y is equal to 1. Right. Key things. Vector equation. Cartesian. Now, so option 1, option 2. Now, option 3 comes to this. Now, Edexcel don't use this, but you can say, if you're on this plane, much like with the equation of a line. For the equation of a line, you start at a point and you add on your direction vector. The idea for a plane is you start at a point and you go, basically you get to travel along these two vectors. So long as you stay on these two vectors, you will stay on the plane. So you start at a point on the plane, 1, 0, minus 1, say, that one. Why? Because it's the first one I can see. And you start adding on multiples of your two direction vectors. And again, I'm going to simplify this direction vector down, minus 1, 1, minus 1, plus mu lots of minus 1, 1, 3. Okay, this is less useful, if I'm honest with you. I find this a lot less useful. It's quicker. It's a lot quicker. That is this version of the equation of a plane. This is very much vector. It is not used in Edexcel. C isn't undefined. C here is just 0. It needs to be 0. It needs to be 0. Okay, so you absolutely can. It's just the main exam board done in the country doesn't use it. And it's not that useful. I don't really like it. You would not get marks for this third form in Edexcel. So this one is not Edexcel. Last I checked. At least it's not useful. Last I had a look. I don't teach it. I don't like it. I think it's silly. Let me just triple check this. 175, 180. Oh no, Edexcel is in there. I just don't use it. It is in there. I just never use it. It is in there. I just don't use it. So instead of saying not Edexcel, it's just not useful. Right? To be fair, it's been ages since I've even seen it in an exam question. That's probably why, because I mostly spend my time doing exam questions, and I haven't seen it in one properly in quite a while. Quite honestly, I think it's possibly because I did OCRB for a longest time, and it's not in OCRB, possibly. I can't remember. Right. Now, what's quite useful here is if you've got this idea of a perpendicular, this is super quick, right? Part C, find the equation of the plane perpendicular to the normal vector and passing through the point. That is super easy. It is r dotted with 2, minus 1, 3 is equal to the point minus 1, 0 dotted with 2, minus 1, 3, which is 2x minus y plus 3z is equal to 1. Yep, thanks guys. It is in there. I found it very quickly. Oh, I need to go review my lists of what's in different exam boards. So you don't even need a random value of z, right, Liam? If you know the normal vector, we're going to use this. R dot n is some constant. And to get the constant, you just need to plug a point in and you're all done, right? You're all sorted. Quick and easy and simple. The age is coming. To be fair, I've taught a number of exam boards across different iterations, and I think it is starting to catch up with me. Very rarely does someone teach all of the modules across all of the exam boards, and there's a good reason for that. How I got the j component, right? The j component, just do the determinant here. -1 times 3 minus -1 times -1 is -4. But again, we do need our pluses and minuses. Remember, plus, minus, plus, minus, plus, minus, plus, minus, plus, all of that gubbins. All right, all of that needs to be in there, and it works out. Okay. I suggest you spend a bit of time going and checking up on the vector product. Right, intersections. And this is why having this particular form for a line for the plane is far, far nicer than the other one that we had. All right. The reason being is that, let's have a look. Let's find the intersection of this line and this plane. So the line is, and if I actually spell this out, the equation of the line is xyz is, if I write this out slightly differently, 2 minus lambda, minus 1 plus lambda, and 3 lambda. All right, playing around with the vectors a little bit. And your plane is 3x plus y plus 2z equals 13. And the idea is, when you find intersections, is I need to find lambda, the value of lambda that makes sure that these satisfy that equation. The issue is that with this form of the equation of a plane, you'll pick up an unknown from the line and 2 unknowns from the plane. It is mental. And you basically end up with 3 simultaneous equations. It is not good for anyone. No one enjoys it. Let's not do that. So what do? I'm going to plug that into there. So 3 times the x plus the y plus 2 times the z has to equal to 13. So let's tidy that up. That's 6 minus 3 lambda minus 1 plus lambda plus 6 lambda is 13. So that is 4 lambda is equal to 8. So that tells me that lambda is 2. So where is the point? The point of intersection will be 2 minus lambda, 0, minus 1 plus lambda, 1, 3 lambda, 6. And you will notice that that is on this line. It's the point on this line where lambda is 2. And if you plug that in, 0 plus 1 plus 12 is 13. Bosh. So line and a plane is super simple. Okay, the equation of a line and a plane. If all the lambdas cancel out, what does it mean if the lambdas cancel out and it's impossible? What if you can't solve it? What does it mean if there's no solutions? How could a line not intersect a plane? Well, yeah, they would be parallel. I think lines and planes, we would describe them as parallel, I think, rather than skew. But yes, you could have a plane and a line just being parallel to it. If there's infinite solutions, then it's on the plane, which is interesting as well. Right, so you could get, say, something like, so if the lambdas cancel, you've got 2 options, right? Option 1, you could get 2 equals 0, say. That's impossible, which is no intersections. And you could end up with everything cancelling out. Everything cancels, all the numbers, everything cancels. There are infinite solutions. So the line is on the plane. Okay, those are options. So those are the two options, India. So if you get something that's impossible, like all the lambdas cancel out and you're left with a number, so 2, and that has to be equal to 0, then that means that's impossible. There are no intersections. But if everything everywhere cancels, you're just saying everything is possible. This will always work. So the line is on the plane. How about the intersection between two lines? Same idea, right? They have to have the same x coordinate. They have to have the same y coordinate. And they have to have the same z coordinate. Simple as that. Now, the key to this is to just pick 2 of them. Pick any 2 equations because I've got 3 equations with only 2 unknowns. Why is that? Well, you have to get quite lucky for 2 objects to crash in midair, right? Like the amount of places where it's possible for 2 lines to not meet far exceeds the number of possibilities where 2 lines meet. Because the point is I can make any of the x and y's or the x and z or y and z, I can make them equal. That's fine. It's just simultaneous equations. However, does that mean they will automatically meet in the 3rd dimension? No. So we're going to pick any 2 of them. It doesn't matter at all. I'm going to tidy them up a little bit. So lambda minus 2 mu equals 5. And this one is... lambda minus 2 mu is equal to 5. So that's unfortunate. So basically, how have I managed this? They are both the same. So that's interesting. So let's try 2 and 3. So let's try 2 and 3 instead, which is 3 lambda minus mu is equal to 5. We can solve those. We get 2 lambda is 0. So I get lambda is 0. Nope, that was a lie. That was the biggest, fattest lie anyone has ever uttered. That was the biggest lie anyone has ever uttered, and you didn't hear me say that. So 3 lambda minus 6 mu is 15. 3 lambda minus mu is 5. We're going to subtract them. I will get 5 mu is minus 10. I'll get mu is minus 2. So I get lambda is 1. Lambda is 1, mu is minus 2. Nick was utterly boogan, but he caught himself before it was too late. Nick was utterly boogan. It's too hot for Nick's brain. So that will make the y and the z coordinates the same, right? These lambda and mu's will make the y and the z coordinates the same. I get mu is plus 2. Minus 2. And that seems to work. You need to check the last one. So we're going to check the first equation. So 2 minus lambda is 1, and minus 3 minus 2 times minus 2, let's put it here, minus 3 minus 2 times minus 2 is also equal to 1. They have to be the same. You will get the same x coordinate here. That's not what I wanted. So check, check, they intersect. You will absolutely lose marks if you don't check with the last equation. So the point of intersection will be at lambda is 1, mu is minus 2. So let's finally give the actual point of intersection. Lambda is 1. 2 minus 1, 1. Minus 1 plus 1, 0. And 3. And again, to make sure you haven't mucked up or done a nick, put your minus 2 into here. Put mu is minus 2 in here right now. Minus 3 plus 4 is 1. 4 minus 4 is 0. 4 minus 2 is 3. Bosh. Does 0 equal minus 1? Why would 0 equal minus 1, dude? Right, now let's try that with C. Oh, I haven't done C yet. Stop it. Right, we're going to do the same one. 2 minus lambda has to equal to minus 3 minus 2 mu. Minus 1 plus lambda is 3 plus 2 mu. And then 3 lambda has to equal to 5 plus mu. So again, we're just going to pick two of them, and I'll do the same thing actually. I'll pick 2 and 3. So that is lambda minus 2 mu equals to 4, and 3 lambda minus mu is equal to 5. What I will do is I will multiply the top one by 3. 3 lambda minus 6 mu is equal to 12. 3 lambda minus mu is equal to 5. If I subtract them, 5 mu is negative 7. Mu is negative 7 over 5. Well, that's plenty. That is disgusting. That is absolutely disgusting. Negative 7 over 5. Oh, well. That will give me lambda is 6 over 5, is it? Lambda is 4 plus 2 mu, so 4 minus 14 over 5. Yep, that's 6 over 5. But what we do is we check in number 1. So 2 minus lambda becomes 10 over 5 minus 6 over 5 is 4 over 5. Write what you're saying, not what you're thinking. And minus 3 minus 2 mu is minus 15 over 5 minus 12 over 5 is very, very much not the same thing. So this tells me that they do not intersect. My 7s can't look like a 1. That's why I put a bar through the 7s, right? My 1s are just vertical lines, and I put bars through the 7s. I feel like I'm getting ganged up on, personally, and it's hurting my confidence. I'm going to open the window, though. I'm dying. Hopefully we don't get too much sound from outside. All right, so line in a plane, super chill. 2 lines, either they meet or they don't meet. Either they meet or they don't meet. And someone did mention that a very quick check to see if they meet, what is quite good, is do a quick check to see if they are parallel. So you can very quickly see if they are parallel. These ones are obviously not. Minus 1 times 2 is minus 2. 1 times 2 is 2, but 3 times 2 is not 1. But you can very quickly check to see if the direction vectors are multiples of each other to see if they are parallel. Do you have to show it's not parallel? Well, no, because if they're parallel, you shouldn't be able to find a point of intersection. If they are parallel, I think in some cases you will end up here, but it's impossible to do. It's impossible to do. So I wouldn't worry too much. It's just a nice quick check at the beginning. A clue for that might be a question tells you to, if it says do 2 lines intersect and it's only like 2 marks, I would check to see if they're parallel, right? Check for something obvious if it's a very low number of marks compared to what the amount of work would be. Oh dear, that was a lot one. Right. Oh, I've just rammed all of these on this one slide. I had actually given myself plenty of space to do all of them on these 3 slides, so apologies there. I'd forgotten I'd done that. Thank you, Parsnick. I ignored you completely, lol. So hopefully you've been able to keep up with that. I give myself loads of space here for it. Right, now, angles between lines is very, very simple. All right, angles between lines. Say you've got one line here and you've got another line here. The only thing that we really need for the angle between them is the angle between their direction vectors. And we're going to pretend that I'm actually able to line some stuff up properly. All right, but all we need is the angle between, hang on. Okay, just checking. So we just need the angle between their direction vectors. Now, this one here, we've got a direction vector. That's all really chill. -1, 1, 3. What we want here is to write this as the vector equation. It's a little bit easier. So remember, that's minus minus 3. So it's -3, -4, sorry, -3, 4, 5, plus mu lots of, and the direction vector is the denominators. So it's telling me that I've got -2, 2, 1 as the direction vector there. Oh, shut up. Okay, so what we've got is that has to equal to square root of 1 plus 1 plus 9, the modulus of this vector. The modulus of this vector, 4 plus 4 plus 1, cos theta, and we're up and running. So that is 7 is root 11 root 9, also known as 3 times cos theta. Cos theta equals what's wrong with the one? Honestly. Oh, this is going to be in degrees now because you all complained about it not being in degrees. We're not going to be friends by the end of this. You realize that, right? 45.3 degrees. And I've kept it in degrees because I'm lazy right now. Okay. The dot product is it in the formula booklet? I don't really spot. We'll have a look later. Remind me later. I've got it as a PDF open here, but just for time. Tonino, right? I heard you. Intersection of planes. I actually don't have that in there. We'll talk about it. Yeah. Let's have a look. So we'll talk about that in a sec. Yeah. Guys, it's 8 hours for all of Core Pure. There are limits to what we can pull off. Okay. Right. Now the angle between a line and a plane. The important thing for the angle between a line and a plane is as follows. For a plane, you have a normal vector. Hopefully you are starting to see why I don't really use that other formulation for the equation of a plane, because it's just purely not useful. So what we are going to do is we are going to basically find the angle between the normal vector and the line. That's what we are going to do. That is essentially what we are doing. We are finding the normal vector between the line, the angle between the normal vector and the line. But the actual angle that we want is here. That is the angle between the vector and the plane. So really what we're doing is we are going to find phi and do 90 minus that. You can do that a little bit quicker because of the way sines and cos works is basically you could just do it straight away with an arc sine. All right, so it's one or the other. You can either just do it with cos and do 90 minus, or you can do it with sine straight away. Up to you. So direction of the line, -1, 1, 3. Direction of the plane is 3, 1, 2. 3, 1, 2, in case you are wondering. 3, 1, 2, 3, 1, 2. That is equal to root 11, root 14. Now, you can either say sine theta or cos phi on this diagram. Up to you. Completely up to you. I've listed it with sine theta because it's actually quite elegant, but there we go. 4. Why is there a blue line by my head? It's my thinking line. It's because it's my thinking line. (18.8 degrees). And you could have done it with cos phi, and you would have got phi. What? What? You would have got phi 71.2 degrees if you did it with cos instead. Right, let me just check where we are at. Okay, let's find a bit of space. I'll do the planes here, okay? So you've got three planes, right? You've got three planes. A1x plus B1y plus C1z is D1. You've got three planes. Now, what this comes down to is a few simple things. Either this can have one solution, it can have zero solutions, or it can have infinite solutions, this system of equations. Oh yeah, thank you. All right, so this is what's going on here. All right. Now, one solution is simple. If there's one solution, if there's only one solution, because basically, if you are trying to find where three planes intersect, you've got three simultaneous equations, three unknowns, x, y, and z. Bosh. So if there's only one solution to this, right, it also tells me that the matrix is non-singular. So A1, A2, A3, B1, B2, B3, C1, C2, C3, that is not equal to 0. So that the determinant is not equal to 0, you should find one solution. There is one point of intersection. Okay, X, Y, Z. Done. Right? So this is non-singular. That's nice and easy. But what if, now we've got two options. If the determinant is 0, there are a couple of things that could happen here. So there could be infinite solutions. So option 1, there are infinite solutions. Now, how could that happen? How could that happen? It's all about the right-hand side. Now, basically, if you try and solve this, you will be able to cancel something out. All right. It's hard to explain, but if you try and solve it, some stuff will cancel out. And basically, the right-hand side has to agree with the left-hand side. And what's going on here is basically, if you look straight on, your three planes meet as what we call a sheaf. And what you've basically got is we are looking straight down where the three planes intersect. And there is a line of intersection. You end up with a line of intersection. Okay, that's where you end up with there. You end up with an intersection line going all the way down, right? So your planes meet like that, and another one coming in like that. So my picture here is you basically viewing straight down my hands, right? And you've got that line of intersection coming straight down the middle there where they meet. So that is how that will happen if you have infinite solutions. There are multiple ways you could have zero solutions. There's two ways you could have zero solutions. One of them is simply if two of the planes are parallel. Two of the planes are parallel. So that would be no solutions. To do that, you just need to check their normal vectors, right? If they are parallel, they will have the same normal vectors or normal vectors that are parallel to each other. So that is an option. That is an option. If two of the planes are parallel, you could have no solutions. It's impossible. It will be impossible. And I'll quickly throw together an example up here in a second, right? So this is no solutions, right? It's in my no solutions part. Or you could have them forming like this. If they're not parallel, what could have happened is you could have them forming like a triangle like this. Again, we are looking at my planes edge on. We are looking at my planes edge on. A triangular prism. Very nice, Mohammed. Very nice. So very quickly, unless I get very, very unlucky here, x plus 2y plus z equals 4. 3x plus y minus z is equal to 3, and minus x plus 3z plus 3y plus 5z is equal to 7. This is absolutely fine. If you check this, it has one solution. Absolutely lovely. One solution, right? And it's actually the 0.111. Okay, so that is case number 1. Let's have a look at this idea of infinite solutions. So I can easily look at some infinite solutions here. So if I've got x plus 2y plus z is equal to 4, then I'm going to get 3x plus y minus z, actually, I'll do this slightly differently. Minus 2z is equal to 3, and then I'm going to get 4x plus 3y minus z is equal to 7. Okay, so I'm going to, these should work. Now, what I mean, right, what I want to do here is very quickly illustrate to you what I mean by the left-hand side agrees with the right-hand side. If you have a look at the left-hand side of this one, the reason this is singular, if you do the determinant of 1, 2, 1, 3, 1, minus 2, 4, 3, 1, you will see that 1 plus 2 is equal to 3. Line 1 plus line 2 is equal to 3. X plus 3x is 4x. 2y plus y is 3y. Z minus 2z is minus z. Okay? Well, if you check the right-hand side, 1 plus 2 is equal to 3. They agree. That will be a sheaf. That will be a sheaf. There are infinite solutions. Basically, what we're saying is equation 3 is redundant. Equation 3 is completely redundant. Okay? Whereas if you look at this case here, it's the same left-hand side. The right-hand side, 1 plus 2 is not equal to 3. So in this case here, right, basically this equation here utterly contradicts this one. So in fact, if I did equation 1 plus equation 2 minus equation 3, I think I would get 0 equals 1, which is impossible. So that tells me I have either two planes are parallel or I've got my triangular prism. That's what that means. Okay? So basically, as soon as we're in the case where the determinant is 0, what it's telling me that on the left-hand side, at least on the left-hand side, one of the equations is redundant. It's not needed. It's just a repetition of the other ones. Okay? Then it's all about, does the right-hand side agree? If the right-hand side does agree, it's because they're forming a sheaf and you end up with infinite solutions. There's a line of intersection. You will end up getting that. Otherwise, check to see if they are parallel. These case, none of them are parallel. 1, 2, 1, 3, 1, minus 2, 4, 3, minus 1. None of those normal vectors are parallel. So in fact, in this case here, so this one would be a sheaf, and this one would be a prism. Hopefully that makes sense to you. All right. So I reckon we're going to overrun by a solid 30 minutes at least. Hopefully you're going to hang around with me for that. That would be lovely. But hopefully that gives you a very quick breakdown. I hadn't planned on it, but good call. I'll add it in for next year. Intersections of plane. Right. angles in, sorry, that was that one. Distances in 3D. Now, first of all, distance from a point to a line, and distance from two lines, and distance. Now, I think it's the same thing, right? Yes. See, I've seen it coming. So no solution for prism, no. Now, distance from a point to a line. You can do this using the cross product. And in fact, if you are doing one of those modules, but I'm going to do it without the cross product. It's actually not too bad. It's actually not too bad. 3, 3, 0. Now, what I'm going to do is I'm going to rewrite my equation here, 2, 1, minus 1, in terms of the I want the vector equation of my line. And you're going to want to do this anyway. You're going to want to do this anyway, no matter which way you do it. So 1, 2, minus 2. And actually, this is a point, so let's just do that. And the idea is this. The idea is this. We're going to just take a generic point on our plane. So a generic point on our plane will be 2 plus lambda, 1 plus 2 lambda, minus 1 minus 2 lambda. All right, much like we did previously, this is now the line r is 2, 1 minus 1 plus lambda 1, 2 minus 2. All right. Now, what we're going to say is we're going to take the vector that joins these two things. We're going to take the vector that joins these. Well, that is shocking, isn't it? Let's take the vector that joins these 2 points. So the vector that joins these 2 points, 3 is minus 1 plus lambda, is minus 2 plus 2 lambda, is minus 1 minus 2 lambda. Do that point minus that, or that minus that, I don't care. And the idea is this: the shortest point, the shortest distance occurs, obviously, when that, we're gonna, Joe, y'all are so impatient, just chill, right? I'm working on it. I just haven't drawn it yet because I'm saying this is a generic point. I haven't made it perpendicular yet, right? This is a generic point, so it is not necessarily perpendicular. And the idea is I'm gonna make it perpendicular. So I want this blue vector to be perpendicular to the black one. So I'm going to force that to happen. And like I said, for a point and a line, it's actually not that bad doing it without. It's actually not that bad doing it without the cross product. So I want that to be equal to 0. So minus 1 plus lambda, minus 4 plus 4 lambda, plus 2 plus 4 lambda has to equal to 0. So that's 9 lambda minus 3 is 0. That gives me lambda is a third. All right, so the actual point that I want is that lambda is a third. So that will be 2 plus a third is 7 thirds. 1 plus 2 thirds is 5 thirds. Minus 1 minus 2 thirds is minus 5 thirds. I do believe. I do believe. I believe. Okay. And then, or simultaneously, we could also just say that the vector joining them is minus 1 plus a third, which is minus 2 thirds. Minus 2 plus 2 thirds is minus 4 thirds. And minus 1 minus 2 thirds is minus 5 thirds. And what we want is actually our distance will be the modulus of that, is the modulus of that vector. Which is square root of 2 squared plus 4 squared plus 5 squared over 3. So what's that? That's 20, that's 45. That's root 45 over 3, which is root 5? Which is root 5. That is very, very much the not using the cross product way of doing it. Now, simultaneously, I'm going to make this a little bit smaller. So I'm going to set myself up here again. I'm going to quickly do it using the cross product. And it goes a little something like this. This time, I'm going to actually find the vector that joins these two up. So 2 to 3 is a 1, 1 to 3 is a 2, minus 1 to 0 is a 1. That is my vector. My direction vector of this line, we said, was 1, 2, minus 2. And the idea goes a little something like this. All right. What we would quite like here is D is the length of this vector. So the length of this vector is quite easy to do. That's root 6, right? The length of that vector is root 6. Length of that one is root 6. Well, the distance that is root 6 times sine theta. Because we're doing a bit of improv. Okay, so the distance is root 6 times sine theta. So you could even do this with the dot product, right? You could find angle theta. We've just been doing it. So you could find the angle theta. You could then find sine of theta, and you could rock on with that. But sine theta is actually 1, 2, 1 crossed with 1, 2, minus 2 over root 6, root 9. Square root of that one, modulus of that one, modulus of that one. And it's modulus of that. Is that easier? Go figure. Go figure. All right. I'm not sure. Okay. We are using the fact that A crossed with B is mod A, mod B sine theta. We're using this fact here that the modulus of the cross product is AB sine theta. That is largely what I'm doing here. That is largely what I'm doing. I'm using that fact right there. Okay, so this is the fact that if you are happy using the cross product, this is a fact that we end up using quite a bit. This is a fact we end up using quite a bit. And you can try it out, right? If I do 1, 2, 1 crossed with 1, 2, minus 2, I will get minus 6, 3, 0. Now, we are absolutely free as well, by the way, to turn that into minus 2, 1, 0. That will work absolutely. So D becomes, it should just become the length of that, root 5. Actually, no, that's not going to work. So it becomes the modulus of this over the modulus of that one. And you get the answer straight away. Okay? So that is another way to do it. But for those of you doing Edexcel and haven't done the cross product, this is how we're going to go about that. All right, but this is a super cool idea. This is a super cool idea. Is the first method easier? It depends how happy you are cross-producting. Right? It depends how happy you are cross-producting. Now, the shortest distance between two lines, we're going to do something incredibly similar. Now, it's going to look like my lines might meet, but they won't. Trust me, I promise. Okay, it's just doing 3D pictures in 2D is a bit tricky. So what we're going to do is we are just going to find a point on this plane. So a point here is minus lambda, 1 plus lambda, 1 minus lambda. A point on this plane is, on this line even, plane, noob. 5 plus 4 mu minus 2 mu, 2 plus 3 mu. And what we are going to do is we are just going to find a line that joins them. And we're going to go, okay. We're going to find a line that joins them. So that is 5 plus 4 mu plus lambda. 1 to minus 2 is, 1 to minus 2 is minus 3, minus 2 mu minus lambda. 1 plus 3 mu plus lambda. So that is the vector. And what we're going to do is we are going to make it be perpendicular to both lines. All right, so as you can see, this is very much the same thing again. Just because of, I really don't care. I don't need to justify myself to you. I'm going to put my direction vectors that way. And yes, I'm getting fighty. All right, so I've got two unknowns, and what I know is that 5 plus 4 mu plus lambda minus 3 minus 2 mu minus lambda, 1 plus 3 mu plus lambda, dotted with minus 1, 1, minus 1, has to equal to 0. So if we tidy that up, it's minus 3 lambda, minus 9 mu, minus 5, minus 8. Do check this for me, please. Lambda plus 3 mu is equal to 3. And we also know that it needs to be perpendicular to the other line if it's going to be the shortest distance. My hand is cramping. Is your hand cramping too? Is this hella tedious? Yes. Yes, it is. It is absolutely tedious. I agree with you. It is horrific. No one enjoys it. And if I'm honest with you, it doesn't get any better using the cross product, in my opinion. Oh no. Has something gone wrong? Oh no. Oh no. Yeah, sorry. That should be a minus 3 on that side. But at this point, I think we just go to this bad boy. Oh, oh, oh. Check this bad boy out. It comes out with lambda is 0, mu is minus 1. Never been more excited. It's almost as if I made this work. So again, what are we doing? We're just taking a generic vector between the two lines, and we're saying, well, if it's the shortest distance, that vector needs to be perpendicular, and we make it perpendicular. So what this vector becomes then is mu is minus 1. So 1, minus 1, minus 2. That works. So my distance then becomes the modulus of that, which is 1 plus 1 plus 4. So I reckon the distance here, the shortest one, is root 6. That is root 6. So that is my answer. Okay. Won't fib, I am not a big fan of the cross product way of doing it for the distance between two lines. You can do it. I'm not going to do it right now because we're overrunning, but if you know how to do it, go check out the formula for it. But it's basically, I'm going to end up doing it, aren't I? Stop it. You can't make me. Right. You do end up using a dot product. You do end up doing a dot product. If we aren't dead by the end of it, we'll come back and do it. All right. Oh, do we have to? Do we have to? All right. All right. All right. All right. All right. 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 The way to do it with the dot product is you take your 2 points that you know are on the lines. You take your 2 points that you know are on the lines. Okay? And we're going to join them up. And we're going to join them up. And I'll do it in green. I'll do this one in dotted green. All right, we're going to join them up. So that vector there is 5 minus 3, 1. 5 minus 3, 1. And the idea is this. The one that we want, the shortest distance here, again, has to be perpendicular, So what we do is we're going to find a vector that's perpendicular. So we're going to find a vector that's perpendicular to both lines. How do I do that? I take the cross product of the two direction vectors. 3 minus 2 is 1. Minus 4 minus 3 is minus 1. Minus 2. And hopefully that works. We had it there anyway. Silly me. Silly me. So cross product gets me the vector that is perpendicular to both of them. All right. In this case, it just works out beautifully. But if you think of that there, right, our distance that we want, our distance is the length of this vector, right, is the length of, our distance is going to be the length of 5 minus 3, 1 cos theta. Well, yeah, but that is just 5 minus 3, 1 dotted with 1 minus 2 divided by the length of 1 minus 1, 2. So divide that by root 6. So that is 5 plus 3 minus 2 over root 6, which is root 6. And that is our, that. So that is us using the cross product, if you will. That is us using the cross product. It is quicker, but it's not in the formula book. I think OCRB might have this one in the formula book. OCRB might have that one in the formula book, but we basically use and abuse these two facts. We use and abuse the fact that the modulus of A cross B is mod A mod B sine theta, and we use and abuse the fact that A dot B is mod A mod B cos theta. And then you basically create a right angle triangle and a bit of SOHCAHTOA. Distance from a point to a plane, this one is given to you. It's right here. It's super simple, super nice. So it's going to be basically you rearrange this to make it equal to 0. To find the shortest distance, you plug the point into there. And you divide by the length of the normal vector. A dot B equals the magnitude of A times the magnitude of B cosine theta. A cross B equals, etc. So I think that's 2/3. Super simple, you get given that one. You can just sub it in simples. Right, before we all die of exhaustion, let's crack on. Reflecting a point in a plane. Now, this largely works, like if you get the idea of the geometry behind this, it's largely fine. So how are we going to do it? Say I've got my point up here. So here I've got the point 1, 3, minus 2, and I've got my plane. The idea is as follows. What we're going to do is we're going to create a line that is perpendicular to the plane. We're going to create a line that is perpendicular to a plane. Well, that's super easy because, of course, this is the plane R dotted with 1, 2, 2 is equal to 5. So we do know, right, we do know that the vector 1, 2, 2 is perpendicular to the plane. The vector 1, 2, 2 is perpendicular to the plane. So what I'm going to do is I'm going to create a line that goes through 1, 3, minus 2 and is perpendicular to the plane. So plus 1 lambda 1, 2, 2. So that's now my dotted blue line. What I'm going to do is I'm going to find out where does it meet the plane. So I'm going to make it meet the plane. I'm going to make it. All right. And you can't stop me. So how do I do that? We've done that. I'm going to plug this into the equation of the plane. 1 plus lambda plus 6 plus 4 lambda minus 4 plus 4 lambda has to equal to 5. So that's 9 lambda. Oh no. Plus 3 is 5. Is that right? Nick has had a lot enough of the cross product. Yeah, I think that's okay. So lambda is minus 2/3. Oh, you get 8 over 9. I get 2 over 9. Actually, I've put minus 2 over 9. It should just be 2 over 9, but 2 over 9. 2 over 9. Yeah, 2 over 3. Lord knows where that came from. I don't know where the 3 came from. It's 2 over 9. I've been saying 2 over 9. I've been thinking 2 over 9. Right. So the geometry of this is, it takes 2/9 of lambda to get me to the plane. So to get to my reflection, I go another 2/9 until I get to my reflection. And that's the plan. So let's recap what the geometry we did there. We said, well, if I want to reflect this point in this plane, what do? I found the equation of a line that goes through the point and is perpendicular to the plane. Easy. I get the normal vector from there, the point there. Simples. And what I do is I go, well, let's see how many lambdas are required to get me onto the plane. And then I'm going to go another lambda. I'm going to go the same again on the other side. If you understand the geometry of how you're adding these vectors together to travel along the plane and the line, sorry, it becomes super easy. Bear in mind, not once in any of these have I used that lambda and mu definition of a plane. I'm just trying to defend the fact that I don't like it. Okay, so my point of intersection will be 1, 3, minus 2 plus 4/9. I plugged this into the plane. So 1 plus 4/9 is 13/9. 3 plus 8/9 is 31/9. Oh. Minus 18 plus 4. Okay. I think that's okay. Again, it's getting rather warm. I'm in a hoodie and actually the hoodie part was easily fixed. Right. Reflection of a line in a plane. Reflection of a line in a plane. Okay. Sort of similar. Sort of similar. If I keep saying sort of similar, will you believe me? Who's going to talk me through how to reflect whilst I desperately try and clear up a bit of space? I'm going to look up at the chat in a second and I'm going to have a full breakdown of how to do this. Yes, absolutely, if you haven't done this. The Z corner is minus 10/9. It could be at this point. I won't lie to you. It absolutely could be. Yeah, it is minus 10/9. Thank you. Right, you find the intersection, then you take any other point on the line and reflect it, then it's just the line joining the 2 points. Absolutely smashing. So let's go through that in a bit more detail. It does require a bit more work, and I might not do all of it. So we got our point. Boop, we got our line right there. Actually, that is just a terrible, terrible, terrible picture for what we're trying to do. Let's try and do that differently. Let's really accentuate this. There we go. I much prefer that. Okay. So we've got our line, and it goes through the points 2, -1, 2. So what are we going to do? So first things first, we're going to find the point of intersection. We are going to find the point of intersection. So again, this is the line is 2 plus 4 lambda -1 -3 lambda 2 plus 4 lambda. And the plane is x minus y minus z equals 4. You put them together and I get 2 plus 4 lambda plus 1 plus 3 lambda minus 2 minus 4 lambda is equal to 0. I am going to go insane if I don't swap that out. So that is 3 lambda. Oh, why do I do this to myself? Lambda is negative 1/3 according to me. Lambda is minus 1/3 according to me. So 2 minus 4/3 is 2/3. Minus 1 plus 1 is 0. Ooh. And then 2 minus 4/3 is 2/3. Okay? And then the other thing we need to do is we do exactly what we just did. And I'm not going to do the whole problem because of time, but we're going to do the exact same thing we just did, right? And we know that one of the vectors on here is the vector 1 minus 1 minus 1. We're going to do the exact same thing. We are going to reflect this point in the plane, and then we can join them up. Then we can join them up. Okay? Right. Last one. Oh, come on. And that was it. I'd given myself all the space in the world to do this, and I've crammed it again. Well done me. Well done me. Well done me. All right. Anywho, that's the idea. So I'm just going to give you the quick spiel again. If you are, this is largely, I won't fib, guys. If you're not doing Edexcel, this is probably not for you. All right, these next bits are not for you. There is a lot of overlap, but it's not perfect at all. All right. So whereas for our main course, this is much better for normal maths. For further maths, it doesn't quite work. But if you're doing Edexcel and you want to join us and you aren't already signed up to my normal lessons, whether you attend them live or not, do check out the link I'm about to put on for the rest of this week. It will also give you access to yesterday's recording, today's recording, the full recorded solutions to the core pure paper, as well as for every single of F1, FM1, FS1, FP1, D1, a practice paper, a session with myself or Guy or Joe, everything recorded solutions, all of that. Okay, all of these things. So we did the pricing yesterday, but it's £49 if you just want to do further maths. Chances are, if you're signing up for this, you're also signing up for maths, then it drops down to £79, which is a big saving. And if you're also, say, doing, pulling out of my head, bio or physics, right, then it becomes only £33 for each subject. Well worth it. Okay, if you figure that one out, it's another 8 hours of lessons in further maths plus the papers, plus about an hour of recorded solutions for each one, it works out pretty darn well. Now, on top of that, so that is our QR code for you to get there. You can always come back and scan that. As well as that, if you've enjoyed hanging out and doing this over Easter with us, do check out the exam masterclasses. I spoke about it earlier, but here is the main thing. We're going to be looking at exam technique, tips and tricks, exam style questions, right up to your exams. All right. I have 15 odd years of teaching experience. You've been hanging out with me now for 8 hours. You get the vibe of who I am, what I'm about. I've told you before, each exam comes with a 3 week before revision session where we go through tips and tricks and everything of an evening. It shouldn't clash with any other exams. And then you get your revision work, it's not a workbook, your revision guide with the spec breakdown, where to find questions, where to find examples. And then on top of that, you get the night before cram session, 4 to 5 hours. So here's the pricing again. It goes down the more you do. Obviously, and funnily enough, if you are doing maths, further maths, and say physics, it becomes quite affordable. Okay. So the video solutions are, if you are signed up, it should be on the platform. It will come live. So the solutions to the paper are linked in the part 2 course, which is the part of the paid, if you sign up for everything I've just spoken about for the Easter revision. All right. So that is on this link here. If you're all signed up for that, you should have access to the part 2 of our Easter revision on the MyEdSpace website, which will have the recordings for yesterday, the recordings for today, as well as the solutions. That should all be on there for you. If not, please reach out to customer services. We'll figure that one out for you. All right. And as I babble, I'm going to leave this up here for those of you wanting to do the exam prep. If you are rocking up on Saturday for FP or for FM or any of that, then I will talk about this in some more detail then, but do check out our QR code. Yep, if you're signed up to the main course, everything, ERC, exam masterclass, that's all part of the main course. In fact, because of how frequently the further maths modules come out, basically the exam masterclass is the main course for the rest of the year. So we've got 2 more weeks of D1, then we've got a week of just general further core revision. After that, basically the last 5 weeks of the MyEdSpace year will just be exam masterclass. You get all of that. The cram the night before is part of the masterclass. I'm afraid you can't access without doing the masterclass. It's all one big thing, right? The masterclass is the pre-revision session, the revision booklet, and the cram. You're not Cook Mohammed, but I would start doing some past papers if I were you. All of you, it's been great fun hanging out. It's been absolutely amazing. I've had great fun yesterday and today. I'm looking forward to some stats tomorrow. Anyone put a big capital S in the chat if you're hanging out to do stats with me tomorrow. No octonauts now. No, I think I can have a little bit of a breather outside in the sunshine. Then I've got to finish prepping stuff. Okay, got some people hanging out to do stats tomorrow. Bosh, some chi-squared, some central limit theorem. We'll do some negative binomial, some probability generating functions. Isn't it going to be fun? We're going to have loads of fun. So that's tomorrow, Thursday. Friday will be further mechanics. Saturday, further pure with me. And then you get the amazing Joe on Sunday for decision maths. Bosh. How do you join the stats, sir? So, CubeCore, if you're not already, I'm going to put this back onto... no, that's the exam masterclass. There we go. If you want to join the rest of the Easter revision course, this is the link here. If you use the same email that you used to sign up for this free session, it should automatically know what options you've chosen and take you through into how to upgrade into the full week. So if you if it's not on your dashboard and you have signed up, make sure you are on part 2 of the exam masterclass. Let me just quickly see if I can make this work. Right, so I'm gonna move this up here. All right, there's a part 1 and a part 2. This is the teacher version, but part 1 is free. You should have access to that. If you've signed up for the paid course, there will be a part 2. So it's 2 separate courses. GCSE Foundation, you have Joe tomorrow for the foundation course. Thank you, Matthew. Thank you. It was great fun today. There should be a separate course. So there's 2 Easter revisions for Further Maths Cube Core. Go find it. There should be a part 2, and that one will have all the rest of it in it. So the stats for AQA and Edexcel are fairly different. Yeah. They are fairly different. Just making sure that I'm not showing you anything you're not supposed to see. I mean, it's not too bad, but for example, we'll be covering the Spearman's correlation, and unless I'm very much mistaken, AQA doesn't do any correlation, I think. AQA doesn't do correlation, so we'll be covering that. And there's a few other bits and bobs. But like chi-squared is covered for both of them. We'll do a bit of no, we're not going to cover any combinatorics if you do OCRA. We will not be covering continuous random variables, for example. For Edexcel, that's in Further Stats 2. It's split up. Like I said, AQA, you cover so much, so that won't be in there. Yeah, so it doesn't correlate particularly well for stats, I'm afraid. We will be covering probability generating functions, which I don't think is a thing for you. So there's a few hiccups, but you know, the core stuff we will be covering. All right. Tell you what, I'll give you a quick breakdown of what we are going to cover in mechanics. Quick breakdown of what we're going to cover in mechanics. Collisions in 1D, elastic, inelastic. So just conservation of momentum, collisions, Newton's coefficient of restitution. So E, we'll do that in 2D on inclined planes, 2 particles colliding, all of that goodness. There's all the stuff with elasticity. So Young's modulus, elastic potential energy. In all of that, there's conservation of energy. So systems moving around, energy lost to friction, a ball goes down a slope, it gains kinetic, loses potential, etc. And work, energy, and power. That is by and large what we are doing. And by and large, that is exactly what we're doing. So it looks to me in AQA, it looks to me like in AQA, there's a bunch of stuff that we would cover that you don't. Is there anything that you cover that? No. So dimensional analysis we don't cover. We won't cover circular motion. We won't cover centers of mass. We don't cover. Right. So yeah, like I say, this is the last bits is very much Edexcel. It is pretty easy, but there is a whole bunch of stuff we're not. If you want to know exactly, hang on, let me go here. So tell you what, let me do this quickly. I don't know how this is going to paste into the chat. Right, that's too big. So let's do it one by one. And then I'm going to hop off. Nope. Not letting me. It's not letting me. Only 100 characters. Yeah, that doesn't come out particularly nice. So for further stats, we're doing discrete random variables, expectation theory, Poisson distribution, geometric, inverse binomial, negative binomial, sorry, hypothesis test, chi-squared, goodness of fit, contingency table, central limit theorem, PGFs, and error and size and power of test, which is a little bit unique. Further Mac, all the momentum stuff, work, energy, and power, elasticity, conservation of energy, and collisions in 1D and 2D. Further pure, we'll be covering L'Hopital's rule, Taylor series, series solutions, differential equations, Leibniz's theorem, conic sections, which again, I think is not in all the other specs. Reducible differential equations, I love that. The T formulae, both for solving and for integrating. Numerical solutions to differential equations, love me a bit of that. One of the most useful bits that you learn. Simpson's rule, and so numerical integration, and the cross product, funnily enough. So a lot of overlap there. And then D1, there's algorithms, graphs and networks, Dijkstra's theorem, Floyd's theorem, route inspection, traveling salesman, and the simplex. On that note, I have kept you for half an hour longer than we had agreed to. So boys and girls, that is it from me. Hopefully you've had a fun couple of days. I will see some of you tomorrow, some of you on Saturday. Otherwise, is there a way to just get the stats and MechStream Cube Core? If you sign up, so you just need to sign up for the rest of the exam. So the rest of the ERC using this QR code. It's equivalent to all our other subjects, right? You get half the course for free in terms of the stream. You get the other half the streams. You've done 8 hours of pure. No matter which 2 modules you choose, you will get another 8 hours of lessons, plus 2 exam papers, plus all the solutions, plus. Okay? Because you're doing AS level. I don't think there is. You can always reach out to customer services and ask them if there's anything they can do. But as far as I have not got any bundle prepped myself for just the AS content, I'm afraid. So the further mech, further stats is all of further mech is all of further stats. There's no AS further mech. There's no AS further stats, I'm afraid. Hello, GCSE A-Level Math 2025. I'm very well, thank you. I'm about to hop off because I'm parched, I'm dehydrated, and I need some more squash. See you for the rest of the week. Otherwise, thank you so much for hopping on and enjoying our streams the last couple of days. Thank you all of you for being helpful and telling me when I've made a little whoopsie. I'm going to head off.